London, 1692, a winter evening, the kind that arrives before 4 o'clock and does not lift until almost 9 the next morning. In a room in Greenwich on the south bank of the Thames, a man named Edmund Halley is sitting at a desk staring at a compass. The needle is pointing north. This is what compass needles do, but Halley knows because he has spent years gathering data, because he has compiled the records of navigators across the world, because he has compared readings from different decades and found a pattern that disturbs him, that it is not pointing exactly north, it is pointing slightly west of north, and it is doing this everywhere, and the direction of the deviation varies from place to place, and the deviation itself changes over decades. The compass is lying, not randomly, not because the needle is flawed or the compass case is magnetic, systematically, predictably, in a way that varies with location and changes slowly over time in a pattern that Halley has been trying for months to explain. Why would a compass lie? For a man in 1692, this is not a trivial question. The compass was the most important navigational instrument in existence. Ships crossed oceans using it. The British Empire, just beginning its long expansion, depended on the reliability of the compass needle to place its vessels where its captains believed them to be. If the compass was systematically wrong, sailors were systematically in the wrong place, and the sea charts were systematically incorrect. This was not a problem of academic interest. It was a problem of enormous practical consequence. Halley has a hypothesis. It is an extraordinary hypothesis, one of the most ambitious proposals about the structure of the Earth that anyone had ever formally written down. Tonight, he's going to finish the paper that explains it. He dips his pen, he writes, and the hollow earth enters the record of science. This is the story of that idea, where it came from, what it attracted, what it inspired, and what finally, 2.5 centuries later, ended it. It is a story about how people reason about things they cannot see, and what happens when brilliant minds encounter the edge of what is knowable with the tools they have. It is, in the end, a story about the inside of the Earth, both the inside that Halley imagined, which does not exist, and the inside that actually exists, which is stranger than anything he proposed. The candle in his room burns down, the pen moves across the paper, outside the Thames moves in the dark. The compass needle holds its slight deviation from north, as it always has, as it always will. Halley does not know why. He will spend years trying to find out. And the inquiry he begins tonight, the careful, honest, wrong inquiry, will eventually lead, by the long route that wrong inquiries sometimes travel, to the correct answer. That is where this story is going. But it begins here, in this room, in the winter of 1692, with a man and a compass, and a question that the world does not yet know how to answer. Find somewhere comfortable. If you haven't already, let yourself settle, adjusting the pillow, pulling the blanket to wherever it feels right, letting the weight of your body soften into the surface beneath you. There's nothing that needs your attention right now. The tasks of the day are finished, or they are as finished as they're going to be tonight, and either way they belong to tomorrow. Right now, the only thing available to you is this: a quiet voice, a long story, and the slow approach of sleep. What I want to tell you tonight is one of the strangest and most genuinely interesting stories in the history of science. It is a story about a wrong idea, a comprehensively, fundamentally wrong idea about the physical structure of the planet you live on. And it is a story about how that wrong idea attracted some of the smartest and most careful thinkers of the past 400 years, and how it survived for centuries after it should have died, and what it eventually gave way to. The idea is this, that the Earth is hollow, not hollow in a minor sense, not riddled with caves, not containing large empty chambers here and there, hollow in the most extreme possible sense, a thin shell of rock surrounding a vast empty interior, with room enough inside for an entire world, complete with its own ocean, its own atmosphere, and perhaps even its own sun. And not just hollow, but inhabited, containing a civilization, or the remnants of one, or the possibility of one, or at minimum a wilderness as rich and strange as anything found on the surface. This idea was not a fringe belief in some dark corner of history, muttered by dreamers who could not distinguish imagination from reality. It was proposed, in all seriousness, by the man who discovered the comet that bears his name, Edmund Halley, Fellow of the Royal Society, personal friend of Isaac Newton, one of the most careful observers of the natural world in the 17th century. It was taken up and elaborated by Leonhard Euler, the greatest mathematician of the 18th century, a man whose collected works fill more than 80 volumes and whose notations we still use today. It was petitioned to Congress by a retired army captain named John Cleves Symmes, who gathered 500 signatures and very nearly got a government-funded polar expedition launched to find the openings. And it was imagined in vivid detail by Jules Verne and Edgar Rice Burroughs and a dozen others whose fictional hollow earths were so compelling that readers found them more real than the real Earth, and that some of those readers, when they put the books down, began to wonder whether the fiction might be fact. Tonight I'll take you through all of it. We'll sit with Halley at his desk in Greenwich, watching his compass needle and wondering why it moves. We'll follow Euler through his calculations of a hollow interior, proposing an inner sun to explain the auroras. We'll travel to the American frontier with Symmes, watching him lecture to sceptical crowds about the polar openings, convinced with the complete conviction of someone who has worked out the geometry and cannot see where it fails. We'll read Verne at his writing desk in Paris, surrounded by the actual geological papers he consulted to make his imaginary underground as scientifically credible as possible. And we'll watch, in the 20th century, as the seismographs finally spoke, as the earthquake waves travelling through the planet's interior returned an answer so clear and so consistent that the hollow Earth could not survive it. By the time we're done, the Earth will be dark outside and your breathing will have slowed, and the story will have descended as far as it goes, to the centre of the actual Earth, to the solid iron core that sits 6,000 kilometres beneath your feet, slowly turning in the dark, generating the magnetic field that makes the compass needle move and the aurora glow and the planet's surface possible. The story starts in 1692 with a problem that nobody could solve. Let yourself settle into it. There's no hurry. The night is long, and the story is rich, and sleep will find you somewhere in the middle of it. The world in 1692 was very different from the one you know, but the people in it were not fundamentally different from you. They had the same mix of careful reasoning and wishful thinking, the same desire to understand what was hidden, the same impulse to fill the unknown with something, with a picture, a model, a story, a hypothesis. They were limited by the tools available to them, as all people in all eras are limited by the tools available to them. They were working at the edge of what could be known, and the edge in 1692 was in a very different place from where it is now. Edmund Halley, at the edge of what could be known in 1692, was one of the most capable minds of his generation. He had already done things that placed him among the significant figures of science. He had catalogued the southern stars, he had correctly calculated the return date of the comet that would bear his name. He had helped make Newton's Principia Mathematica possible, editing it, funding its publication, arguing Newton into completing it when Newton was inclined to abandon the project. He was, in other words, not someone prone to foolish ideas. He was someone who had demonstrated repeatedly the ability to look at evidence and reach correct conclusions. And he looked at the evidence of the drifting compass needle and reached an incorrect conclusion. This is worth sitting with, because it is the heart of what makes the hollow Earth story interesting and ultimately instructive. The incorrect conclusion was not random. It was specific, it was reasoned, it was internally consistent, and it fit the available evidence. It simply was not correct. And the reason it was not correct was not that Halley was careless or biased or foolish. It was that the correct answer required information that had not yet been gathered. This is, I think, one of the most important things the Hollow Earth story has to teach. Not a scientific lesson about planetary structure, but a lesson about the nature of knowledge. Correct conclusions require correct information. Correct information requires the right tools to gather it. The right tools require the right scientific development to produce them, and scientific development is slow, cumulative, dependent on the contributions of many people working across many generations. There is no shortcut through this process. There is no way to reach the correct answer before the tools exist to gather the necessary data. All you can do is work with what you have, hold your conclusions honestly, rather than claiming more certainty than the evidence warrants, and leave the question open for the next generation to approach with better tools. Halley did all of this correctly. He held his hypothesis as a hypothesis. He gathered more data. He published what he had. He left the question open. He was wrong about the answer. He was right about the method. And the method, in the end, is what matters. Because the method is what eventually produced the right answer, 2.5 centuries after he asked the question. That is the story tonight. It is, in the end, a story about patience, about the long time it takes for hard questions to receive complete answers, about the people who live in the middle of that long time, who ask the questions before the tools to answer them exist, who propose the hypotheses that will eventually be replaced by better ones, who keep the inquiry alive through periods when the inquiry seems to be going nowhere, about the people who eventually arrive at the end of the long time with the right tools and the right data and the right answer, and who know when they arrive that they are standing on the shoulders of everyone who asked the question before them. The story starts in 1692, settle in. To understand why Edmund Halley proposed what he proposed, you have to understand the compass problem. Not just that it existed, the compass problem had existed for as long as sailors had used compasses, but why, in the late 17th century, it suddenly felt urgent enough to demand a new kind of explanation. This was not a new annoyance. It was an old annoyance that had begun, through the patient accumulation of records across several generations, to reveal a pattern. And patterns in the mind of a scientist are not annoyances, they are invitations. Compasses had been in regular use in European navigation since roughly the 12th century. Before the compass, sailors relied on stars, on the sun, on wind direction, on the colour and temperature of the water, on the behaviour of birds. All of these methods worked well enough in familiar waters, under familiar skies. They became unreliable in bad weather, at night in cloudy conditions, in unfamiliar seas. The compass solved those problems by providing a reference direction that did not depend on visibility, a needle that pointed consistently toward something in the north. Except that it did not quite point toward true north. It pointed toward magnetic north. And magnetic north, as anyone who had sailed widely had noticed, was not where true north was. The angle between where the compass pointed and where the North Star sat in the sky differed depending on where you were on the Earth's surface. This angle, the magnetic declination, had to be known and corrected for if you wanted accurate navigation. Sailors learned the correction for their home waters. Charts were annotated with it. The problem was manageable. The problem that was less manageable, and the one that occupied Halley, was that the correction was not fixed. It changed. Not rapidly. You would not notice it within a single voyage, and perhaps not within a single career at sea. But over decades, the comparison of compass records from the same locations told a consistent story. The needle had moved. The magnetic declination at London in 1580 was significantly different from what it was in 1640, which was different again from what it was in 1692. The difference was not small. At London, the declination had gone from roughly 11 degrees east of true north in the 1580s to approximately 6 degrees west of true north by the time Halley was writing, a swing of 17 degrees over a century. This was not a navigational curiosity. This was a navigational problem. Charts annotated with magnetic declination corrections became unreliable over time, and a navigator relying on an old chart without accounting for the drift could find himself significantly off course, not by the small amounts that good navigation skills might catch and correct, but by amounts that could put a ship on rocks or shoals rather than in a safe harbour. The secular variation of magnetic declination, as it came to be called, secular meaning long-term, not short-term, was a genuine practical concern. But it was also, to a mind like Halley's, a scientific mystery. Why did it drift? What was happening inside the Earth or above it or around it that could produce this slow, systematic shift in the direction of magnetic north? The mystery demanded an explanation, and the explanation Halley reached for was the only one available to him: the construction of a model of the Earth's interior that could produce the observed behaviour. Edmund Halley was not simply a man who happened to notice an interesting pattern. By 1692 he was one of the most respected scientific figures in England, and his reputation was built on exactly the kind of careful, patient data analysis that the compass records represented. He had corresponded extensively with Isaac Newton. He had financed, out of his own pocket, the publication of Newton's Principia Mathematica when the Royal Society ran short of funds. an act of intellectual patronage that is perhaps the most consequential investment in scientific publishing in the history of the field. He had computed the orbits of comets, tracking 24 of them, and noticing that certain historical comet sightings corresponded to the same orbital path, leading him to propose that they were the same comet returning, the comet that now bears his name. He was a person whose scientific credibility was substantial. When Halley turned his attention to the compass problem, he brought to it the same methodological approach he brought to everything. Gather as much data as possible, look for patterns, propose a model that explains the patterns, and submit it to the critical attention of the scientific community. The Royal Society, founded in 1660 and already the preeminent scientific institution in England, was the natural venue. Its Philosophical Transactions was the journal where serious hypotheses were published and scrutinized. The model Halley proposed in 1692 was this: the Earth is a hollow sphere. Inside the outer shell on which we stand, there are additional spheres, nested one inside another. He specified 4 inner spheres in the final version of his paper, though the exact number was somewhat flexible across different drafts and discussions. These inner spheres are separated from the outer shell and from each other by gaps, distances perhaps comparable to the distance between the Earth and the Moon, perhaps smaller. Each inner sphere carries its own magnetic poles, and each inner sphere rotates, but not at exactly the same rate as the outer shell. This differential rotation, the inner spheres turning at slightly different speeds than the outer shell, is what produces the secular variation. As the inner spheres slowly drift in their rotation relative to the outer shell, their magnetic poles drift too. The needle of every compass in the world, responding to the combined magnetic influence of the outer shell and all the inner spheres, swings slowly in response to this drift. The pattern of drift observed in London and in Paris and in the southern hemisphere all fit, in Halley's analysis, a model in which the inner spheres were rotating at specific rates relative to the outer shell. It is worth pausing here to note what kind of argument this was. It was not speculation. It was not fantasy. It was a quantitative hypothesis, one that made specific numerical predictions about the rate of drift and the pattern of its variation across different locations on the Earth's surface. Halley was not simply proposing that the inside of the Earth was interesting. He was proposing a specific internal architecture and arguing that this architecture would produce the observed patterns in the data. The hypothesis was testable. It predicted things that could be measured. The proposal also included one additional element that has attracted attention ever since. Halley noted that if the inner spheres existed, they might be habitable. He was careful about this. He described it as a possibility rather than a claim, and he grounded it in the theological reasoning of his time. God, who had created so much space in the universe, would presumably not have wasted the interior of the Earth on mere emptiness. If there was room for life, there might be life. The inner spheres, separated from the outer by gaps potentially hundreds of miles wide, might be lit by some form of internal luminosity, a persistent glow sufficient to support existence of some kind. This was not as wild a proposal in 1692 as it might seem today. The astronomical revolution of the previous century had profoundly expanded the conception of the universe. Jupiter had been found to have moons, Saturn had rings. The Milky Way was understood to be composed of individual stars, each potentially a sun, each potentially with worlds of its own. The assumption that Earth was the only inhabited world was already being questioned by careful thinkers, not as mysticism, but as rational inference from the scale of what the telescope had revealed. If the universe was vast enough to contain many inhabited worlds, why should the inside of our own planet be simply blank? Halley submitted his paper, and it was published in the Philosophical Transactions in 1692. The title was formal and careful, an account of the cause of the change of the variation of the magnetical needle, with an hypothesis of the structure of the internal parts of the Earth. That word hypothesis was important. Halley knew he was speculating. He was not claiming to have visited the interior. He was claiming that the interior, as he had modelled it, would produce the observations he had catalogued. The response from the scientific community was not ridicule. It was engagement, which is the appropriate response to a well-constructed hypothesis. Some scientists found the model plausible, others had objections. The discussion continued in the years following publication, as Halley gathered more data and refined his model. he made further observations of magnetic declination across different parts of the globe, particularly during a voyage in the Atlantic from 1698 to 1700 that he undertook specifically for this purpose, one of the first scientific expeditions in history, a voyage not for trade or conquest, but for measurement. The Atlantic voyage produced something remarkable, the first magnetic declination chart, showing the variation of the compass across the entire Atlantic Ocean. The chart was precise, based on careful measurements taken at hundreds of locations. It was also, in its way, a monument to the compass problem that had started everything. A map not of coastlines or depths, but of the invisible field that bent the needle, rendered visible through the patient work of observation. Halley never found direct evidence for his hollow Earth model. The inner spheres remained undetected, because no instrument then available could detect them. The compass continued to drift, exactly as his model predicted it would, which was consistent with his hypothesis but not conclusive. A consistent model is not the same as a confirmed model. Other explanations remained possible. The internal architecture of the Earth remained, as it would remain for another 2 centuries, a matter of inference and proposal rather than observation. But the question was now in the public record of science. The interior of the Earth had been formally proposed as a domain of scientific inquiry, with a specific hypothesis on the table that could be tested, refined, or replaced as better data accumulated. The candle burned down. Halley set aside his papers. The winter cold of his room settled back around him, and somewhere in the dense dark below the foundations of his house, below the soil and the clay and the bedrock of England, below everything reachable by any tool he had, the Earth continued its ancient processes, entirely unchanged by the model proposed above it. The model was wrong, but the inquiry it launched was right, and the two things, a wrong model and a right inquiry, are more closely related than they might at first appear. Sometimes you need the wrong model to ask the right question. Sometimes the wrong answer is the thing that points you, eventually, toward the right one. Let the room grow quiet. Let the image of the compass needle fade. That slight deviation from north, that persistent refusal to point exactly where it is told to point. The needle was telling the truth about something. It took 2 more centuries to find out what. That is not an unusual gap in the history of what we know. It is worth dwelling for a moment on what the Atlantic voyage meant in practical terms. In 1698, Halley was given command of a Royal Navy vessel, the Paramore, a small pink-rigged sloop, and sent to sea under orders from the Admiralty to measure magnetic declination across the Atlantic Ocean. He was not a naval officer. He was a scientist being given authority over a vessel and crew to pursue a scientific objective. This was unusual. The Navy was not in the habit of lending ships to natural philosophers. That it happened at all reflects how seriously the problem of magnetic variation was taken by the institutions that cared about navigation and trade, which meant, in England in 1698, the institutions that cared about empire. The voyage was not smooth. Halley had difficulties with his first lieutenant, Edward Harrison, who questioned his authority and his decisions. Harrison had his own ideas about navigational science, and apparently made no secret of his low opinion of the captain's seamanship. The dispute became serious enough that Halley eventually ordered Harrison to desist, and filed a formal complaint upon returning to England. He was given command of a second expedition in 1699, this time without Harrison, and that expedition was more successful. During the second voyage, Halley pushed further south than the first expedition had gone, reaching below 50 degrees south latitude and approaching waters that Europeans rarely visited. He saw icebergs in these southern seas, massive flat-topped tabular bergs that were different from the ice he had expected. He noted their characteristics and their location carefully, because they were a navigational hazard that deserved documentation, regardless of what else was being measured. The magnetic measurements continued throughout. Thousands of compass readings, recorded at precise locations, building the picture that would become the first declination chart. When he returned from the second voyage in 1700, Halley had the data he needed to construct his chart. The result, published as a new and correct chart showing the variations of the compass in the western and southern oceans, was immediately useful to navigation. Ships crossing the Atlantic could now look up the expected declination at any given location and correct their compass readings accordingly. The practical value was real and immediate, regardless of whether the theoretical explanation, the nested spheres, was correct or not. Good data in service of a wrong model is still good data. This is perhaps the clearest illustration of why Halley's Hollow Earth deserves to be remembered without embarrassment. He was doing something genuinely valuable. The Atlantic expedition was a model of what scientific inquiry could accomplish: careful, patient, systematic, willing to travel to dangerous and unfamiliar places to gather the evidence needed to test a hypothesis. The fact that the hypothesis proved wrong in its structural details does not diminish the quality of the inquiry. It simply means the inquiry was honest enough to be wrong. Leonhard Euler was, by most measures, the greatest mathematician who has ever lived. This is not a casual assessment made for narrative effect. It is not a compliment offered in the customary way that popular histories offer compliments to their subjects. It is the considered opinion of mathematicians themselves, people who do not give praise easily, who deal in proof and in precision, who are constitutionally suspicious of superlatives, because superlatives, by definition, cannot all be true at once. When mathematicians rank their own kind, Euler sits at or near the top of any serious list. He produced more mathematics than any other person in recorded history. His collected works fill more than 80 volumes. He worked so prolifically and with such apparent ease that his contemporaries sometimes suspected he was not quite human, that something moved through him that did not move through ordinary minds. He was born in Basel, Switzerland in 1707, the son of a Calvinist minister who was himself an amateur mathematician and who recognized early that his son's relationship with numbers was different in kind from the ordinary competence of a well-educated man. Euler studied with Johann Bernoulli, one of the leading mathematicians of the age, and Bernoulli recognized in him something he had not seen before. Not just ability, but a kind of mathematical instinct, a way of seeing structure in problems that others saw only as complicated noise. At 19, Euler submitted his first paper to the Paris Academy of Sciences. At 20, he left Basel for St. Petersburg, where Peter the Great had founded the Russian Academy of Sciences and where brilliant young Europeans were being recruited to populate it. The St. Petersburg years were enormously productive. Euler contributed to number theory, to the theory of infinite series, to the calculus of variations, to mechanics, to optics, to music theory. Yes, music theory, which he approached with the same systematic rigour he brought to everything else. He introduced, or standardized, much of the notation that mathematics still uses today: the letter e for the base of the natural logarithm, the letter m for the square root of -1, the letter pi for the ratio of a circle's circumference to its diameter, the use of f of x to denote a function of x. These seem like small things, mere conventions, but they are not small. They are the shared vocabulary that allows mathematics to be communicated clearly across languages and centuries, and Euler invented or systematized most of them. When he was 26, Euler lost the sight of his right eye. The cause is uncertain, a fever perhaps, or an abscess behind the eye. He reportedly commented on the loss with characteristic pragmatism, suggesting that it would reduce his distractions. Whether this was genuine equanimity or a public performance of equanimity, we cannot know. What we know is that his output did not decrease. If anything, it increased. The internal mathematical landscape that he navigated apparently required no external light to remain visible. At 59, living in St. Petersburg for the second time, he had spent many years in Berlin before returning to Russia at the invitation of Catherine the Great. He lost the sight of his remaining eye. An operation to remove a cataract left him completely blind. He was given 3 weeks of sight immediately after the operation, as the wound was healing, before inflammation set in and the darkness returned permanently. In those 3 weeks, he apparently memorized as much as he could of his working environment, the positions of objects in his study, the layout of the house, the faces of his assistants. Then the darkness came back and stayed. In the 17 years between his complete blindness and his death in 1783, Euler produced almost half of his total lifetime output. He worked by dictating to his son and to a succession of mathematical assistants. He held problems in his memory with a clarity that seemed to others almost supernatural. Long chains of calculation that most mathematicians would need to set down on paper simply to keep track of. He had trained his memory over 60 years to serve as a perfectly reliable workspace. Blind, he worked faster than most sighted mathematicians work with their pencils and paper. This is relevant background to the hollow Earth, because it tells you something about the quality of mind that, in 1741, proposed a hollow Earth with a small sun at its centre. Euler was not the kind of thinker who proposed things casually or imprecisely. He did not speculate in the ordinary sense of that word. When he proposed a model of something, he worked through its implications with mathematical rigour, checking whether the model's predictions were consistent, identifying the parameters that could in principle be measured to test it. His hollow Earth was not a whim. It was a hypothesis subjected to the kind of scrutiny that Euler applied to everything. Euler's version of the hollow Earth was structurally simpler than Halley's. Where Halley had proposed nested spheres, a whole internal architecture of rotating shells, each with its own magnetic poles, each rotating at its own rate, Euler imagined a single hollow cavity, roughly 800 miles across by some of his estimates, with a miniature sun hanging at the centre. This inner sun, he reasoned, would provide heat and light to the interior surface. It would create convective air circulation, warm air rising near the poles, cooler air flowing along the equator, a weather system on the inside surface driven by the same principles that drove weather on the outside. The interior could, in principle, support plant life, and plant life could support animal life, and animal life could support intelligent life. Euler was not writing fiction. He was not dreaming. He was working through the physical implications of a premise with the tools available to him. How large would the hollow cavity need to be to permit an inner sun of sufficient luminosity? What would the gravitational dynamics look like on the inner surface? Would inhabitants be pulled toward the outer shell by the mass of the Earth around them, or toward the central sun by its mass? These are real questions, and they have real mathematical structures, and Euler addressed them with real mathematics. The gravitational question is actually interesting even in retrospect. On the inner surface of a hollow sphere, gravity does not work in the simple way it works on the outer surface. A theorem in Newtonian mechanics, Newton's shell theorem, which Euler would have been familiar with, states that the gravitational field inside a hollow spherical shell is exactly zero. If you are standing on the inner surface of a hollow Earth, the shell of rock around you pulls you in all directions equally, and those pulls cancel out. You would not be pulled toward the outer shell the way surface inhabitants are pulled toward the centre. You would be effectively weightless, unless there was some other massive object nearby to provide gravity, which is where the inner sun comes in. Its mass would provide a gravitational centre, pulling the inhabitants of the inner surface slightly toward it, giving them a sense of up and down, oriented not outward toward the shell but inward toward the sun. This is internally consistent. It is wrong, because the Earth is not hollow. But the physical reasoning, within the constraints of the hollow Earth premise, is correct. Euler was applying Newton's mechanics accurately. The geometry of gravity inside a hollow sphere is a real and interesting mathematical problem, and Euler's approach to it was sound. The fact that the premise was wrong does not make the mathematics wrong. This is a distinction that is easy to miss but important. A hypothesis can be false while the reasoning from it is valid. If the Earth is hollow, then the gravitational dynamics of the inner surface would be such that, if the if is false, the then clause may still be mathematically correct. Euler was not making mathematical errors. He was making a factual error about the Earth's structure, which is a different kind of error entirely. Euler published his hollow Earth proposal not as a standalone paper, but as part of a broader work on natural philosophy, what we would now call physics, in 1741. It appeared as one section of a larger discussion, not as a central thesis. This is consistent with how Euler worked. He explored many things simultaneously, treating each as a problem to be analysed rather than a conviction to be defended. The inner sun was an interesting possibility that he explored rigorously, and then set aside, presumably to move on to the next interesting possibility, on a list that was, effectively, infinite. The intellectual climate in which Euler was working made the hollow Earth a more plausible hypothesis than it would seem today. The 18th century was the century of systematic inquiry into the natural world, the century when the principles of Newtonian mechanics were being extended from the motion of planets to the motion of tides, to the behaviour of fluids, to the propagation of light, to the structure of matter. The Earth's interior was, within this framework, simply one more natural system to be described. It was inaccessible, Nobody could go there, but inaccessibility did not, in principle, prevent analysis. You analysed a system from what you could observe, proposed a model that fit the observations, and worked out the model's implications. The Enlightenment faith in reason, the conviction that the natural world was in principle comprehensible, that its workings could be grasped by careful observation and rigorous inference, meant that even inaccessible domains were not off-limits to inquiry. Quite the opposite. They were the most interesting domains because they were the ones where the power of reasoning could be most dramatically demonstrated. To infer the structure of the Earth's interior from compass readings and surface observations alone, to reason from the observable to the unobservable, was exactly the kind of intellectual achievement that the Enlightenment valued most highly. Euler lived and worked in St. Petersburg and Berlin, moving between them as royal patronage shifted, spending decades in each city, corresponding continuously with mathematicians across Europe. He was the most connected scientific mind of his era, known to every serious mathematician and physicist from London to Moscow. When Euler said something, when he proposed a model, when he worked through an implication, when he identified a problem, people paid attention. Not out of deference to his status, though his status was extraordinary, out of justified confidence in his track record. He was right about things at a rate that was simply anomalous. So when Euler proposed an inner sun, the response of the scientific community was not dismissal, it was consideration. The proposal was examined, its implications were traced, its consistency with known physics was assessed. The verdict, in the end, was inconclusive. Not that the inner sun was proven false, but that there was no evidence for it either, and that the hollow Earth model in general made no predictions that could be tested with the instruments available in the 1740s. This is the condition of many scientific hypotheses at their moment of proposal, not confirmed, not falsified, but simply unresolvable with current tools. The inner sun joined a list of proposals that were waiting for technology to catch up, proposals that were logically consistent and empirically underdetermined, floating in the space between the confirmed and the refuted. It would remain in that space for a long time. Euler died in 1783, still working, his mind intact even as his body failed. He left behind a mathematics so comprehensive that his successors spent decades simply sorting through his papers, finding completed proofs he had never gotten around to submitting, identifying patterns he had noticed without explaining, following threads he had begun and set aside. The inner sun hypothesis was a small part of this output, a footnote in some ways, but it had attached to the hollow Earth something that Halley's version had been missing. A mechanism for the interior to be warm and lit, a reason for it to be habitable not just in principle, but in practice. The warm lit interior would become one of the central features of the hollow Earth as it developed through the 19th century, in the fiction that imagined it into vivid detail, in the theories that built on Euler's basic premise, in the popular imagination that found the idea of a sunlit world below irresistibly appealing. Euler had planted a specific image, not darkness, not a cold void, but light. An inner sun, small and warm, hanging at the centre of a habitable space. That image would prove to have a very long life. Let Euler settle into the distance now. The blind mathematician, still calculating in the dark, still finding his way through problem spaces that required no light to navigate. He proposed an inner sun in a world that had no way of testing the proposal, in a spirit of genuine inquiry rather than conviction, and then moved on to the next problem. The inner sun remained, hanging in the literature, waiting to be taken up by someone with the energy and the commitment to do something with it. The next person to do something significant with the hollow Earth would not be a mathematician. He would be a soldier from Ohio with 500 signatures on a petition and a belief so fierce it looked, to most observers, like madness. Before we leave Euler entirely, it is worth noting the physical setting in which he did this work. St. Petersburg in the 18th century was a city being built from scratch on a river delta in the northwestern corner of Russia, an ambitious imperial project designed to announce Russia's presence in the community of European powers. The Russian Academy of Sciences, where Euler spent much of his career, was itself part of this announcement, an attempt to create an institution that could compete with the Royal Society in London and the Académie des Sciences in Paris. The scale of the Academy's ambition exceeded what the population of Russia could easily supply, so the Academy drew in talent from across Europe. Euler, Swiss by birth and educated in Basel, was one of the imports. The isolation of St. Petersburg from the rest of European intellectual life, slow mail, difficult travel, long winters, had an effect on Euler's work that is often underappreciated. He could not easily attend lectures or conferences. He could not easily consult colleagues on obscure points. He was, more than most of his contemporaries, dependent on his own resources for the development of his ideas. This enforced self-reliance may be part of why his work is so systematically comprehensive. He could not rely on others to fill gaps, so he filled them himself methodically, working through implications that a more connected mathematician might have delegated or left incomplete. The inner sun hypothesis, in this context, is exactly the kind of thing Euler would work through during a St. Petersburg winter. A physically interesting problem, proposable from first principles, amenable to mathematical analysis, unlikely to be resolved by experiment in the near future. It is speculative physics done by a mind that could not easily step out for a conversation about the current state of underground geology, so it did what it could with what was available, which was, as always with Euler, a great deal. If you enjoy documentaries like this to fall asleep to, subscribe. I post a new mystery like this every week. Halley and Euler did not invent the idea that something existed below the surface of the world. They formalized it. They gave it equations and submitted it to learned societies and dressed it in the language of natural philosophy. But the intuition that the earth was not simply solid, that something of significance waited below, is ancient, older than mathematics, older than writing, present in cultures across the world in forms so varied and so consistent that it is worth pausing to ask why. Why does every major civilization independently fill the space below the ground with something? Why is the underworld one of the most universal features of human cosmology? Part of the answer is simply practical. People saw things come out of the ground, water from springs, fire from volcanoes, smoke from fissures, sulphurous gases from cracks. They felt the ground shake. They heard sounds that seemed to come from below. The earth was clearly not inert. It was doing things. Something was driving those things. Whatever was driving them was by definition inside the earth. The inference that the inside of the earth was an active place, a place where processes happened, where something existed and moved, was not mystical. It was reasonable. But the mythological underworlds go further than simply positing that the earth's interior is active. They make it inhabited. They give it structure, geography, a social order. They populate it with gods and spirits and the dead. This is a different kind of inference, not from observable phenomena to physical causes, but from the universal human fact of death to a necessary destination. The dead go somewhere. They do not simply cease. And the somewhere they go is, in most traditions, below the ground where they are buried, below the soil that covers them, below everything that is visible and touchable and ordinary. The ancient Greeks had their underworld. They called it Hades, both the place and the god who ruled it. In the oldest traditions, Hades was not a place of fire and punishment. That came later, influenced by other religious currents. In Homer, Hades is grey and still, a realm of shadows populated by the diminished remnants of the dead, the shades who retain the form and memory of life but have lost its substance. They wander in a twilight that is neither dark nor light, neither warm nor cold, in a permanent colourless in-between. The geography of the Greek underworld was detailed enough to suggest that it had been thought about carefully, that it was not simply a vague beyond, but a specific and internally consistent place. The rivers had names and properties, the Styx, across which Charon ferried the dead, demanding payment in the form of a coin placed on or in the mouth of the deceased, which is why the Greeks buried their dead with coins. The Lethe, the river of forgetting, whose waters the dead drank to shed their memories of life, and whose name gives us the word lethargy. The Phlegethon, the river of fire, the Acheron, the river of woe. The landscapes of Hades were also specific. The Asphodel meadows, where ordinary shades wandered after death. Elysium, or the Elysian fields, where heroes and those favoured by the gods resided in a more pleasant afterlife. Tartarus, the deepest level, where the Titans were imprisoned and where the worst sinners were punished in specifically designed ways. Tantalus perpetually reaching for food and water that withdrew from his grasp, Sisyphus rolling his boulder up the hill forever, Ixion bound to a spinning wheel of fire. The entry points to the underworld were identified as real locations on the Greek landscape. Lake Avernus, in what is now southern Italy, a volcanic crater lake that was genuinely toxic in ancient times, its waters releasing sulfur dioxide and hydrogen sulfide in concentrations high enough that birds flying over it fell dead. Virgil, writing the Aeneid centuries after Homer, used Avernus as the entrance through which Aeneas descended to the underworld to consult his dead father. The lake's actual properties, the dead birds, the smell, the absence of ordinary life, made it a plausible portal. Something was coming up from below. If you did not know about volcanic gases, the conclusion that what was below was dangerous, inhabited by powers inimical to the living, followed naturally from the evidence. The Norse tradition had Niflheim, the world of ice and mist that existed below the roots of Yggdrasil, the world tree, in the complex cosmology of 9 worlds. Niflheim was one of the primordial realms, existing before the gods themselves, a place of cold and darkness that predated the creation of the inhabited world. Below Niflheim, deeper still, was Helheim, the realm presided over by Hel, whose name is the direct ancestor of the English word for the same concept, via the Proto-Germanic word for the covered place, the hidden place, the place below. Hel herself, the goddess, was described as half-living and half-dead, the upper half of her body alive and normal in colour, the lower half corpse-coloured, pale and cold. She received the dead who died of illness or old age rather than in battle. Those who went to Valhalla, the hall of slain warriors, did not come to her realm. Her domain was for the ordinary dead, the ones who had not made themselves memorable in battle, and it was in this sense a democratic underworld, a place for everyone who was simply mortal, who lived and aged and died without particular distinction. In Mesopotamia, in the Sumerian and Akkadian traditions that are among the oldest recorded mythologies we have, written on clay tablets that have survived 4,000 years, there was Kur, the underworld beneath the earth. The goddess Inanna descended into it, passing through 7 gates, surrendering an item of clothing or jewellery at each gate until she arrived naked and powerless before her sister Ereshkigal, Queen of the Dead. This descent myth, in its multiple versions across Sumerian, Akkadian and Babylonian sources, is one of the oldest literary narratives we know about, and it is a narrative about what is below, about the existence of a realm beneath the ground that is real and structured and governed by someone. The descent and return of Inanna has been interpreted many ways, as a myth of the seasons, with Inanna's descent corresponding to winter and her return to spring, as a myth about death and resurrection, as a myth about the relationship between the living world and the dead one. But whatever its interpretation, the geography it assumes is consistent. Below the earth there is a place, with gates and rulers and rules of passage, and a person can descend to it and return if the conditions are right. The Egyptians had the Duat, the underworld through which the sun god Ra travelled during the 12 hours of night, navigating through 12 chambers, each with its own character and its own challenges. The Duat was not simply a metaphor for darkness. It was a real place, mapped in careful detail in the Books of the Dead and the Book of What is in the Duat, ancient texts that served as guidebooks for the deceased, providing the words and knowledge needed to navigate the underworld successfully. The solar bark of Rhea moved through the Duat from west to east during the night, doing battle with Apep, the serpent of chaos, in the final hours before dawn. The Duat was underground in a specific sense. It was beneath the horizon, beneath the earth that the living walked on. When the sun set, it did not simply disappear. It went below into the Duat to travel through the underworld and emerge in the east at dawn. The journey was perilous and the outcome was not guaranteed. The battle with Apep could, in principle, be lost, and if it were lost, the sun would not rise. The fact that the sun always rose was evidence not that the battle was unnecessary, but that Ra always won, assisted by the prayers and rituals of the living. The Hindu traditions described Patala, the lowest of the 7 underworlds in the Puranic cosmology, a place of great beauty and wonder rather than punishment. The Mahabharata describes Patala in terms that read almost like a travelogue of an exotic destination. The light there is more beautiful than the light of the sun, because it is not harsh but soft and gem-like. The inhabitants are prosperous and handsome, the palaces are magnificent, the women are beautiful, the flowers bloom without wilting. It is, in this tradition, not a place of the dead, but a place of the living, an alternate world below, inhabited by Nagas, the serpent people, and by other beings of power and beauty. This vision of the underworld as a place of wonder, not merely of punishment or of grey shadow, but of a different and sometimes superior kind of existence, appears across multiple traditions. The Celtic otherworld, Tir na Nog, was sometimes located below the ground and was described as a place of eternal youth and beauty. The underground kingdoms of folklore, the fairy hills, the hollow mountains inhabited by elven beings, were dangerous but magnificent, full of music and feasting and powers that the surface world lacked. The pattern suggests something about how human minds engage with the space they cannot see. The inside of the Earth is a real space, bounded above by the ground we stand on, extending downward for thousands of kilometers. It is real in the sense that there is genuinely something there. But it is invisible. It cannot be directly experienced, and into invisible spaces, human imagination always moves, filling them with something coherent and specific, something that explains what the space must be doing given what you can observe of its effects on the surface world. Halley and Euler were, in this very long view, doing something that human minds had always done, filling the invisible below with a structured, inhabited world. Their version was dressed in the language of the Royal Society and the mathematics of the 18th century. The language was different. The basic impulse was ancient. There is one important distinction between the mythological underworlds and Halley's hypothesis. The myths were not falsifiable. They were not presented as hypotheses in the scientific sense, as models whose predictions could be checked against observations. They were cosmologies, total pictures of the world's structure, held in place by tradition and religious authority, immune to empirical revision in a way that scientific hypotheses are not supposed to be immune. Halley's hollow Earth was falsifiable in principle. It made specific predictions about the behaviour of magnetic declination that could be checked against measurements. If the measurements had come out differently, if the secular variation had not fit the pattern his nested sphere model predicted, his hypothesis would have needed revision or abandonment. The myths had no such relationship to evidence. They explained the surface world's behaviour, the seasons, the sunrise, the presence of death, in ways that were consistent with observation, but that could not, in principle, be ruled out by observation. This is the difference that matters, not the content of what was proposed. The nested spheres are not obviously more plausible than the grey rivers of Hades. But the relationship of the proposal to evidence. Halley was operating in a tradition that required him to show that his model fit the data, and would have required him to revise it if it did not. The myths operated in a tradition that required only internal coherence and traditional authority. The long pre-scientific tradition of underworld thinking mattered to the Hollow Earth story in a subtler way. It had kept the concept of a below-the-world alive in human thought for millennia, making it feel natural rather than extraordinary. When Halley proposed his Hollow Earth, he was not violating anyone's intuitions about the world's structure. He was giving scientific form to intuitions that the entire history of human culture had prepared people to have. The underworld was already real in some sense, already accepted, already assumed, already furnished with detail. Halley was, in this sense, working with the grain of human thinking rather than against it. That ease is part of why the Hollow Earth persisted as long as it did. It was not a counterintuitive idea being forced on a reluctant world. It was a familiar idea being given a new kind of authority. The scientific dress made it more credible to minds trained in the new natural philosophy, but the underlying intuition that something significant was below had been prepared by everything that came before. The myths drift past now. The grey rivers and the serpent people and the 12 chambers of the duat, each one an attempt at the same question, each one shaped by its own cultural moment, its own theological needs, its own emotional understanding of what death and the below must mean. All of them wrong, in the simple factual sense. All of them reasonable, in the sense that they were answers to a real question, assembled from real observations, by minds doing what minds do in the presence of the unknown. The question was never foolish, only the available answers were incomplete. It is worth pausing over one more tradition, one that sits at the intersection of mythology and early natural philosophy, and that represents something like the first attempt to give the underground a systematic rather than purely mythological structure. This is the tradition of cosmological diagrams in medieval European thought, the attempts by scholars working within a Christian framework to describe the structure of the earth in terms that satisfied both theological requirements and the available observations. Medieval European cosmology inherited a complicated legacy. The classical Greek philosophers had proposed a spherical earth, which the educated medieval European accepted. The idea that the earth is flat is, despite its popular reputation, not a medieval belief. The Aristotelian earth was a sphere, and medieval scholars knew it was a sphere and worked with that knowledge. But the sphere in Aristotelian cosmology was surrounded by concentric shells of the other elements, water, air, fire, which were in turn surrounded by the crystalline spheres carrying the moon, the sun, the planets, and the stars. The entire system was nested, hierarchical, organized around the central earth. Within this nested structure, the underground was the center of the earth, the lowest, most dense, most material region. In Christian theological terms, the center of the earth was also the appropriate location for hell, the place farthest from God, who resided in the Empyrean beyond the outermost sphere. Dante's Inferno, written in the early 14th century, is the most famous literary expression of this cosmology, a structured underworld at the center of the earth, divided into concentric circles descending toward the uttermost point of the universe, where Satan himself sat frozen at the center of everything. Dante's hell is, in this sense, a nested sphere cosmology of the underworld, layers within layers, each with its own character and population, each organized around a central point. Halley's Hollow Earth, proposed 3 centuries later, shared this basic structural intuition: layers within layers, organized around a center. The nested spheres of Halley's model are structurally kin to the concentric circles of Dante's hell. The content is entirely different. Halley's spheres are rotating magnetic shells, not circles of punishment, but the underlying structural image of a layered underground with something significant at the center is very old. This does not mean Halley was influenced by Dante. It means that the nested sphere structure answered something deep in the cultural imagination of people who had been thinking about the underground for a very long time, something about the intuition that the underground, like the above ground, should have levels, should have organization, should not be a mere undifferentiated mass, but a structured space with different regions at different depths. When Halley proposed nested spheres, he was giving physical and mathematical form to a structural intuition that medieval cosmology had also expressed in theological form centuries before. John Cleves Symmes Jr. had fought in the War of 1812. He had served as an infantry officer in the American forces, seen action in the campaigns along the Canadian border and the Great Lakes, and survived the war with what his fellow officers described as a reputation for steadiness and courage, in circumstances that would have unsteadied and discouraged many men. He was, by the accounts of those who served with him, exactly the kind of soldier that armies need, and that officers are proud to have commanded: dependable, calm under pressure, committed to the task at hand regardless of its difficulty. After the war ended in 1815, Symmes left the army and turned to commerce. He became a trader in the Missouri frontier, a practical physical occupation requiring the management of goods and transportation over rough terrain, negotiation with suppliers and buyers, and the kind of stubborn persistence that made the early American West livable rather than simply survivable. He was, in every visible respect, a practical man, a man of action rather than reflection, more comfortable with a ledger and a trade route than with a library. And then, in 1818, he sent a circular to every institution he could think of. The circular reached universities and learned societies, members of Congress, foreign governments, newspapers, anyone Symmes thought might be interested in what he had to say. He had had it printed at his own expense, a significant cost for a frontier trader, and distributed as widely as his resources allowed. The text was brief, urgent, and entirely confident. It began, "I declare the earth is hollow and habitable within, containing a number of solid concentric spheres, one within the other, and that it's open at the poles 12 or 16 degrees. I pledge my life in support of this truth, and am ready to explore the hollow if the world will support and aid me in the undertaking." It was signed John Cleves Symmes of Ohio, late captain of infantry. The proposal for which Symmes was pledging his life was built on a model he called the Symmesian theory, or sometimes simply Symmes's system. It differed from Halley's in several important ways. Where Halley had proposed nested spheres with no openings to the outside, a hollow earth in principle accessible only by drilling through the shell, Symmes proposed that the earth was open at the poles. The polar regions, he argued, curved inward at a specific angle, creating vast openings through which a ship could simply sail from the outer surface to the inner. These openings he designated Symmes holes. The inner spheres were accessible from the outside without any drilling. They were, if you knew where to look and were willing to travel far enough north or south, simply there. The polar openings were the feature that made Symmes' proposal distinctive and to many people exciting. Halley's hollow earth was, in a practical sense, inaccessible. You would need to drill thousands of miles to reach it, and no drilling technology could do that. Symmes's hollow earth was in principle reachable with the ships and the navigational techniques that already existed. It was not a theoretical possibility, but a proposed destination, a place you could go. The immediate response to the 1818 circular was, as might be expected, largely negative. Scientists who received it found it unsubstantiated. Symmes had provided no mathematical derivation of the polar opening dimensions, no physical mechanism for how such openings could exist without the Earth's geology producing them, no explanation of why the polar expeditions already undertaken had not found them. The physics were at least questionable. The evidence was non-existent. Scientists had limited patience for well-meaning amateurs who pledged their lives in support of things they could not demonstrate. Newspapers were less uniformly dismissive. Some covered the circular as a curiosity, in the tradition of curious items that newspapers have always found appealing. Some covered it more sympathetically, noting that the man was at least sincere, and that the inside of the earth was, technically, a subject on which the last word had not been spoken. The public response was mixed, but not uniformly hostile. Symmes began lecturing. He travelled from city to city across the young United States, Philadelphia, New York, Cincinnati, Pittsburgh, and dozens of smaller towns, giving public talks about his hollow earth theory to whoever would pay the small admission and come listen. He was not by any account a gifted natural speaker. He was earnest, specific, and clearly passionate, but he was also prone to digressions and repetitions that tried the patience of audiences who had hoped for something more dramatic. What held people's attention was not oratorical brilliance, but the quality of his conviction. He believed, and his belief was total, and total belief has a certain compelling quality, even when the content of the belief is strange. He had read widely in preparation for his lectures. After the war, after returning to civilian life in Ohio, he had worked his way through the available literature on natural philosophy, geology, and polar exploration. He had read Halley. He had read accounts of the Arctic expeditions undertaken by the British Navy in the years immediately after the Napoleonic Wars, when ships and crews newly freed from the demands of European conflict were redirected toward geographical discovery. He had studied the behaviour of animal migrations, noting that certain species seemed to travel toward the poles in winter rather than away from them, a pattern that he interpreted with considerable inventiveness as evidence that the polar regions were warmer than expected, consistent with the presence of an interior opening through which warm air from the inside escaped. The animal migration evidence was in fact misinterpreted. The species Symmes cited were not travelling toward polar warmth, but following food sources that moved for reasons entirely unrelated to interior openings. But Symmes was not simply making things up. He was reasoning from real observations, the migrations were real, toward a wrong conclusion, in exactly the way that Halley had reasoned from real observations toward a wrong conclusion. The methodology, if not the result, was recognizable as an attempt at scientific inference. By 1822, Symmes had gathered enough public support to make a serious political push. He began lobbying Congress for funding for a polar expedition, specifically a voyage to the North Pole to look for the opening he was certain would be found. He was not asking for an enormous sum. A few ships, proper supplies, the authorization to attempt the voyage under naval protection, and with scientific personnel aboard. The petition eventually gathered around 500 signatures, a significant number, reflecting the cumulative effect of his lecture tours and the newspaper coverage they generated. The petition was formally presented to Congress in 1822 and 1823. It was referred to committee. It was debated. Some members of Congress found it worth engaging with seriously. The question of what was at the North Pole was, after all, genuinely open since no expedition had yet reached it. Others found it risible. The debate was not extensive, but it was real. The hollow earth theory had arrived in the legislative branch of the United States government and was being treated as a subject worthy of, at minimum, formal consideration. The vote went against funding, but the margin was not overwhelming, and the fact that there had been a vote at all was significant. The hollow earth theory had been formally considered and formally rejected by the United States Congress. This was not, from Symmes' perspective, an endpoint, it was an episode. He continued. He refined his model in response to objections, specifying the dimensions of the polar openings in more precise terms, addressing the question of how the lip of the opening would appear to navigators approaching it. He proposed that the curvature would be gradual enough that sailors might not realize they had passed through the opening. They would simply find, at some point, that they were sailing on the inner surface rather than the outer one, the gradual inward curve having carried them through without any dramatic threshold. This was a clever response to the objection that no polar expedition had ever noticed any such opening, the answer being that the opening was too gradual to notice without careful instruments and careful observation of the horizon's behaviour. One of Symmes's earliest and most energetic supporters was a man named Jeremiah Reynolds, a newspaper editor and lecturer from Ohio who became something like Symmes's public relations manager, polishing his arguments, managing his correspondence, advocating for his cause in settings where Symmes himself was not present. Reynolds was sharper and more presentable than Symmes, and he was a gifted writer. He composed pamphlets and articles that made Symmes' case more persuasively than Symmes himself could, and he leveraged the connections he developed through this advocacy into a broader campaign for American polar exploration. This is worth noting. Reynolds eventually abandoned the specific hollow Earth hypothesis while maintaining the advocacy for Antarctic exploration. He petitioned Congress separately, on grounds that had nothing to do with Symmes's holes, and his advocacy contributed to the United States exploring expedition of 1838 to 1842, which mapped significant portions of the Antarctic coastline. The hollow Earth theory, in this sense, had a productive side effect even as the theory itself remained unproved. It helped generate interest in a region of the world that would eventually reward exploration with real scientific discoveries, none of which had anything to do with interior openings. Symmes himself never reached the poles. He died in 1829 in Hamilton, Ohio, at the age of 49, still advocating, still corresponding, still planning an expedition that he never assembled the resources to undertake. He was buried in Hamilton, and his admirers, of whom there were more than the scientific establishment would have liked to acknowledge, erected a monument to him in the town. The monument includes a hollow sphere on top, representing his hollow Earth. It still stands. The legacy of John Cleves Symmes is strange and in some ways moving. He was wrong about everything structural. The polar openings do not exist. The inner spheres are not there. His physics were confused, and his evidence was misread. But he had done something that Halley and Euler, writing for learned societies in formal philosophical prose, had not done. He had made the hollow Earth a matter of popular concern, a topic that ordinary Americans felt entitled to have opinions about, a question that was on the floor of Congress rather than merely in the pages of learned journals. He had democratized the question, and while the question turned out to have a different answer than he proposed, the energy he put into keeping it alive, the lecture tours and the petitions and the correspondence and the absolute conviction, contributed to a climate of inquiry about the polar regions and the Earth's interior that eventually, through paths he could not have predicted, led to better answers. Sometimes the people who keep a question alive are the people who are most wrong about the answer. The congressional petition deserves more attention than it usually gets in accounts of the hollow Earth, because it illustrates something specific about American intellectual culture in the early 19th century that is easy to miss from a later vantage. When Symmes gathered his 500 signatures and submitted his petition to Congress in 1822, asking for funding and ships for an expedition to the poles to test his hypothesis, he was not doing something that seemed obviously ridiculous in the context of its time. The American government was actively interested in exploration. The Lewis and Clark expedition had been completed only 16 years earlier. The Wilkes expedition to the Pacific and Antarctic, which would eventually be funded, was already being discussed in some quarters. The idea that the government should fund expeditions to unknown regions was not controversial. The only question was which expeditions were worth funding. Symmes' petition was debated in Congress, not for long, and not with much sympathy from the scientific members, but debated. The representative from Ohio who introduced it was not embarrassed to do so. The letters of support that accompanied it came from respectable citizens. The hollow earth was, in 1822, on the outer edge of serious discourse, rather than clearly outside it. The line between legitimate scientific speculation and fringe belief was not drawn in the same place it would be drawn a century later. This tells us something about how the line gets drawn, not by logic alone, but by the accumulation of evidence over time, by the development of tools that make certain hypotheses testable and others obviously wrong, by the gradual consensus of a community of inquiry. In 1822, the tools that would eventually settle the Earth's interior structure did not exist. The seismograph was 60 years in the future. The concept of plate tectonics was 140 years away. In that context, Symmes's hypothesis was not obviously worse than the alternatives. It was specific, it made testable predictions, and it was based on a real phenomenon, the variation of the compass, the same phenomenon that had moved Halley a century and a quarter earlier. What Symmes lacked was not conviction or specificity. He lacked, ultimately, the luck of being right, and the tools that would have told him convincingly that he was wrong. He died still believing, and still waiting for the expedition that would confirm what he was certain the polls would show. Let the image of Symmes settle and drift. The former soldier, the frontier trader, the self-taught theorist standing at the front of a rented hall in Ohio with his diagrams and his conviction. He was wrong. He was completely, irrecoverably wrong. And the energy of his wrongness mattered. The story is moving now toward the places where the hollow earth becomes not just a theory, but a world, fully imagined, sensory and specific, rendered in language precise enough that readers feel they have almost been there. There is a footnote to Symmes' congressional campaign that rarely appears in histories but deserves mention. One of the senators who voted against funding the polar expedition was John Quincy Adams, at that point still a senator from Massachusetts before his presidency. Adams was scientifically literate and took the question seriously enough to look into it before voting. He voted against, finding the evidence insufficient. But years later, as president, Adams was among those who supported the more general case for American polar and scientific exploration, contributing to the eventual authorization of the Wilkes expedition. The wrong reason for an expedition, finding Symmes's hole, failed to get funding. The right reason, scientific exploration and national prestige, eventually succeeded. The hollow earth route to Antarctic science failed. The Antarctic science still happened. This is perhaps the most succinct version of the hollow earth's contribution to knowledge, not what it claimed to offer, but what it failed to offer in a way that eventually pointed toward what was actually worth offering. The wrong hypothesis, pursuing the wrong opening, motivating attention to a real question, which eventually received a real and remarkable answer. Jules Verne published his novel Journey to the Centre of the Earth in French in 1864. He was 36 years old, the author of several well-received books, but not yet the international figure he would become. The novel tells the story of Professor Otto Lidenbrock, a Hamburg geologist of formidable energy, considerable erudition, and famously short temper, and his nephew Axel, who follow a 16th century alchemist's coded message to a volcanic crater in Iceland, and from there descend into the interior of the earth. What they find below is not Dante's hell, not Halley's nested spheres, not Euler's inner sun, but something stranger and more specific, a vast subterranean sea, lit by the glow of electrified gases, edged by mushroom forests of enormous scale, inhabited by prehistoric creatures, with weather of its own, and a sky of luminous cloud that neither brightens nor dims but simply glows. The science in the novel is meticulous. This is the feature that tends to surprise readers encountering it for the first time, expecting popular fantasy and finding something closer to a scientific treatise with adventure attached. Verne had done his research. He had read the geological literature seriously. He had read the accounts of Icelandic exploration. Iceland was, in the mid-19th century, one of the least explored territories in Europe, and Verne's descriptions of the volcanic landscape through which the characters walk on their approach to the crater are based on real expedition accounts and detailed enough to be verifiable. He had read Humphrey Davy's work on the mineral composition of the Earth's crust, and he had followed the contemporary geological debates about the temperature gradient underground. A debate in which real scientists were genuinely disagreeing about whether the Earth's interior was hot or cold. Professor Lidenbrock is in some sense a composite of every serious investigator who had ever proposed something unusual about the Earth's interior. Halley's methodical data gathering, Symmes' ferocious conviction, Euler's mathematical confidence, all of these qualities are present in the professor, arranged into a fictional character who is simultaneously ridiculous and admirable. He is ridiculous in the way that obsession always has a ridiculous dimension. He forgets to eat when he is excited about a problem. He terrorizes his household with his impatience. He declares certainty about things that are genuinely uncertain. He is admirable in the way that genuine scientific passion is always admirable. He pursues the question with total commitment. He adjusts his thinking when the evidence demands it. He's never defeated by the obstacles he encounters, only by the need to revise. The key scene in establishing the novel's scientific credentials comes early, when Lidenbrock and Axel debate whether the Earth's interior is hot or cold. This was a real scientific debate in 1864. The question of the Earth's thermal gradient and what it implied for the deep interior was genuinely contested. One school held that the Earth was hot throughout, with a molten interior only thinly crusted over, a view supported by volcanic activity and by the observed increase in temperature as you go deeper into mines. Another school, which Werner's Lidenbrock represents, held that the temperature increase levelled off at depth, and that the deep interior might be relatively cool. The novel presents both views seriously, argues for one of them with specific evidence, and acknowledges that the question is not yet settled. This is exactly the right posture for a science-inflected novel, not pretending certainty where there is none, but engaging honestly with the state of the question. Lidenbrock is also right that the descent route exists, and here Verne demonstrates a real understanding of Icelandic geology. The path down through the Snæfellsjökull crater follows a volcanic conduit, a passage through the rock left by old magmatic activity. Such passages are real. They are explored by speleologists, cave researchers, in Iceland and elsewhere. They do not go to the centre of the Earth, of course, but the premise that a sufficiently old volcanic system might have passages going significantly deeper than ordinary caves is not absurd. Verne was reasoning from real geology, extending it beyond what geology supports, while keeping it tethered to actual features of the volcanic landscape. The underground sea that the explorers eventually reach is described with extraordinary sensory specificity. Verne describes the quality of the light, diffuse, sourceless, a glow that seems to come from the atmosphere of the cavern itself rather than from any locatable point. He describes the temperature, surprisingly comfortable, not the hellish heat that the theory of a molten earth interior would have predicted, but something moderate and human scale. He describes the water, without the smell of salt, without the slight bitterness of ocean water, without the weight and pull of tides, a sea that is deeply quiet in all the ways that surface seas are not. He describes the sound, or rather the near absence of sound. The underground sea is quiet in a way the surface ocean never is. There is no wind. No waves break on the shore with the rhythm that surface waves have. The water moves if disturbed, but left alone it is still. The stillness is total. The stillness is what lingers with readers. Verne understood, intuitively or deliberately, that the most evocative feature of the underground world he was imagining was not its strangeness, but its quiet. The surface world is always making noise. Wind and waves and birds and insects and the thousand small sounds of a living, moving world. Below, in the cavern that Verne imagined, there is nothing to make those noises. The quiet is structural. It belongs to the place. It has been there since before anything alive existed to notice it. And in describing it, Verne touched something that readers recognise. Not from experience of underground seas, but from the experience of lying very still, in a room after midnight, when the ordinary noise of the world has faded and something close to real quiet becomes briefly available. The prehistoric creatures are less convincing to modern readers than they were to Verne's contemporaries. The ichthyosaurs and plesiosaurs battling in the underground sea, belong to the scientific mythology of the mid-19th century, when the discovery of fossils was still relatively recent, when the concept of geological deep time was new and exciting, and when the creatures of the prehistoric past felt closer and stranger than they do to us. But the underlying premise, that the deep interior might have preserved conditions from an earlier phase of the planet's history, that it might be a kind of time capsule of the geological past, is more interesting than the specific creatures it generated. It is, in a way, a scientifically serious idea that isolated environments can preserve things that the rest of the world has moved on from. The novel was an immediate success. It was translated into English, German, and other languages within years of its French publication. It launched Verne's international career and established the template for what would become, in the following decades, the genre of scientific romance, stories in which technically accurate or technically plausible science served as the structural armature for adventure and wonder. 20,000 Leagues, Under the Sea, From the Earth to the Moon, The Mysterious Island. All of these grew from the same root as Journey to the Centre, the same conviction that the world was large enough and strange enough that rigorous inquiry into its real properties could produce stories as compelling as any fantasy, and more instructive than most. Verne's contribution to the Hollow Earth story was not limited to the literary. It was also, in a precise sense, propagandistic. It spread the idea, gave it new life, put it in front of an audience many orders of magnitude larger than the audience that read scientific journals or attended lectures. Readers who had never heard of Halley or Euler or Symmes came away from Journey to the Centre with a vivid sense of what the underground might be like, with an image of a subterranean sea that felt, for the duration of the novel, entirely real. The novel did not argue that the Hollow Earth was true. It did not need to. It imagined the Hollow Earth in such specific, grounded detail that readers came away feeling they had almost been there. There is a detail in the novel that tends to get overlooked. Professor Lidenbrock at several points is explicitly uncertain. He does not know what they will find at the bottom of the volcanic conduit. He does not know if the route he has decoded is correct. He does not know if any of them will survive. His public performance of certainty, the bluster and the declarations and the impatience with doubt, is a strategy for sustaining his own courage and his nephew's in the face of genuine not knowing. Underneath the bluster is a scientist doing what scientists actually do when they are doing science honestly, proceeding on the best available hypothesis while remaining genuinely uncertain about the outcome and not allowing the uncertainty to paralyze the proceeding. Verne understood this tension. He had read real scientific literature and corresponded with real scientists. He knew that the presentation of certainty in public, the declaration that this is the answer, that the path is clear, that the evidence is compelling, was often a translation of something more nuanced. This is the best current hypothesis. This is where I would bet if I had to bet. This is the direction in which the evidence most strongly points. He put that tension into Lidenbrock and left it there, without resolving it, because the tension is real, and resolving it into simple certainty would have been dishonest. The novel ends in a way that has sometimes disappointed readers expecting more triumphant conclusions. The explorers do not emerge from the Earth having conquered it or mapped it, or settled the scientific questions it raised. They are expelled, ejected by a volcanic eruption, shot upward through a Mediterranean vent, landing on the slopes of Stromboli with only their notes and their memories, and no proof that anyone will believe them. The underground sea remains on the maps they drew, but the maps cannot be verified. The prehistoric creatures they saw cannot be captured and brought back. The knowledge exists in the heads of the explorers, but it exists in the form of testimony, and testimony, without corroborating evidence, is not the kind of knowledge that science counts. Verne meant this ending. The underground world is real, within the fiction. The explorers saw it and touched it and nearly died in it, and it is as real as anything in the novel. But it is inaccessible in a way that prevents the kind of proof that would satisfy a skeptic. You cannot go back and bring a piece of it out. You cannot point someone else toward it and have them verify what you saw. The knowledge you brought back is the kind of knowledge that cannot be shared in the form that matters, the form of publicly verifiable evidence. This is deliberately a meditation on the limits of exploration, on the gap between experience and proof, on the things that can be genuinely known but not transmitted in a form others will accept. In the decades after the novel's publication, the hollow Earth became a fixed feature of popular culture in a way it had never quite been before. It appeared in adventure stories for boys, in newspaper serials, in popular lectures. Verne's underground sea was the image, not Halley's nested spheres, not Euler's inner sun, but a sea with prehistoric creatures and the smell of salt replaced by the smell of minerals, a luminous sky above and strange cold water below, and somewhere in the distance something large moving under the surface. The image persisted because it answered something that images, rather than arguments, answer. The need to feel what a place would be like, to have a sensory experience of it, rather than merely an intellectual description. Verne gave the hollow Earth a sensory reality, the feel of the cool air, the sound of the quiet water, the specific quality of the sourceless light, that made it available to the imagination in a way that Halley's mathematics had never quite managed. Let the underground sea settle around you for a moment. Still water in a vast space, light from nowhere, air that smells of minerals and time, the silence that belongs to the place, that has been there since before the first thing that could notice it. It is not real. But the person who imagined it with such care that it feels real, he was real. And the care he brought to the imagining was itself a kind of knowledge, a kind of attention to what the underground might be like if it were like anything at all. The next person to imagine the hollow Earth into vivid detail would take Verne's underground sea and add something Verne had not quite included. An entire world, with its own history and its own civilization, its own sun and its own people, waiting in a permanent afternoon for someone from the surface to arrive. Verne's novel remained in print throughout the second half of the 19th century, went through numerous translations and generated a minor industry of imitations and sequels. The underground became, after 1864, a standard literary geography, as settled a location in the imagination as the frontier west or the high seas. Readers who had never thought about the actual structure of the Earth now had a vivid image of what below might be like, and the image, being vivid and sensory and emotionally satisfying, was harder to dislodge than any argument from physics. This is one of the underappreciated powers of fiction. It creates experiential memories that function like real memories. The readers of Journey to the Centre of the Earth had not visited the underground sea, but they had been there, in the only sense that matters to the imagination. They had experienced it sensorially and emotionally in the way that a vivid dream is experienced, and experiential memories are harder to revise with argument than abstract beliefs. You can change someone's abstract belief about the interior of the Earth by presenting seismic evidence. You cannot as easily change the felt sense of a place that they have, in some sense, visited. Verne's novel, in this sense, made the hollow Earth more resilient against the evidence that would eventually accumulate against it. Not because it convinced anyone it was true. Verne never claimed it was true, and most readers understood they were reading fiction, but because it gave the hollow Earth an emotional reality that outlasted its scientific plausibility. When the seismic evidence arrived and the scientific hollow Earth collapsed, the literary hollow Earth remained, still vivid, still available to the imagination, still answering the need for elsewhere that the scientific version had briefly addressed. Edgar Rice Burroughs published At the Earth's Core in 1914, 50 years after Verne's novel, and the interior world he created was utterly different from Verne's underground sea. Where Verne's interior was dark and prehistoric and geologically constrained, a large cavern, ultimately however extraordinary its dimensions, Burroughs was something else entirely, a full world, a second Earth, with its own continents and seas and sky and sun, its own ecology and history and civilizational structure. He called it Pellucidar, and over the next 3 decades he returned to it 7 times, building it into one of the most elaborately realized secondary worlds in the history of popular fiction. Burroughs was not pretending to science in the way Verne was. He had read Verne. He was an avid reader of popular fiction and of the adventure romance tradition that Verne had helped create. And he had absorbed the hollow Earth as a premise from the scientific and popular literature that had accumulated around it. But his interest was not in the geological implications of a hollow Earth. It was not in the physics of nested spheres or the mechanics of polar openings. His interest was in the narrative possibilities, in what you could do with a world that was inside the Earth rather than on top of it, if you let yourself think about it without being constrained by geological plausibility. The premise of At the Earth's Core is simple and is delivered quickly. David Innes, a wealthy young American mining engineer, finances the construction of a mechanical burrowing device, the iron mole, a drill powerful enough to penetrate the Earth's crust, designed by an eccentric inventor named Abner Perry. The iron mole is meant to be a commercial mining tool. On its first test run, something goes wrong with the steering mechanism, and Innes and Perry find themselves drilling uncontrollably downward, deeper than any mine, deeper than any natural cave, deeper than anything they had intended. When the machine finally stops and they push their way out, they are not underground in any ordinary sense, they are inside the Earth. And inside the Earth is Pellucidar. What they find is not darkness. The first thing they see, emerging from the iron mole, is sky. Not the sky above, not the sky of the outer surface, which would be below them, below the shell of the rock they have drilled through. The sky of Pellucidar is above them, the ceiling of the inner sphere, and it glows. Not with the cold blue of an ordinary sky, but with the warm, diffuse light of a world in which the sun hangs fixed at the centre. The sun of Pellucidar does not rise or set. It does not travel across the sky. It sits at the precise centre of the hollow sphere and illuminates the inner surface with unvarying light. On Pellucidar it is always noon. This is the central and most interesting feature of Burroughs' hollow Earth, and it is one he worked out with some care. A sun fixed at the centre of a hollow sphere would illuminate the entire inner surface equally, without shadow, without the variation of morning and evening, without the cycle of day and night that organises life on the outer surface. The implications are far-reaching. Without day and night, there is no obvious way to measure the passage of time. Without seasons, because every point on the inner surface receives the same amount of light from the central sun regardless of the planet's position in its orbit, there is no year. The inhabitants of Pellucidar live in what Burroughs calls an eternal present. They do not age in any recognisable way, because aging is measured against time, and time on Pellucidar has no structure by which it can be measured. This temporal strangeness is not merely a decorative detail, it has narrative consequences. When David Innes and Abner Perry descend to Pellucidar in the iron mole, they leave behind not only the surface world but the surface world's time. The adventures they have in Pellucidar occupy what feels like a long period of experience. But when they return to the surface, in the later books, with some difficulty and some ingenuity, they find that almost no time has passed on the surface. The interior world is in a sense outside of time, or rather it operates on a time that does not correspond to surface time, because the measurement of time requires a periodic phenomenon, and Pellucidar has no periodicity. Burroughs worked the geometry of the inner surface carefully, in a way that reveals he had thought seriously about the spatial implications of his premise. On the inner surface of a hollow sphere, the horizon does not fall away from you, as it does on the outer surface. On the outer surface, the curvature of the Earth means that the horizon is always below you. Things at a distance appear to sink below the curve. On the inner surface, the opposite is true. The curvature curves upward. If you stand on the inner surface and look toward the horizon, the terrain curves upward and away from you, so that in principle, if your eyesight were good enough, or your instruments precise enough, you could see the entire inner surface at once, the continents and seas of Pellucidar curving upward to meet each other above your head. This means that on Pellucidar you're never truly alone. The entire world is always visible in principle, and in practice much more of it is visible than would be visible from any surface vantage point. Mountains on the far side of an inland sea are visible because they curve upward into view, rather than disappearing below the horizon. A person on the opposite side of the world, the point directly above you, the nadir of the inner surface, is not over a horizon, but directly overhead. The scale of the visible world is vertiginous in a way that has no surface equivalent. The inhabitants of Pellucidar are varied. There are primitive human beings, organised into tribes and clans, at different levels of what Burroughs calls development. Some hunters and gatherers, some with the beginnings of agriculture and metalworking, some already building what might become cities. Over them rule the Mahars, great pterodactyl-like creatures of formidable intelligence, telepathic, capable of hypnotizing humans, who have organised the surface peoples of Pellucidar into something resembling a slave society. The Mahars cannot speak. Their speech organs are suited to high-pitched sounds inaudible to humans, but they communicate with each other through a form of mental projection, and have developed a written language and a body of recorded knowledge. The relationship between the Mahars and the human populations of Pellucidar is explicitly colonial, a term Burroughs does not use, and probably did not think about in those terms, but which describes what he depicts accurately. The Mahars regard human beings as useful, somewhat dangerous livestock, tolerated for the labour they provide, culled when they become troublesome, kept dependent and disorganised to prevent them from becoming a threat. David Innes, arriving from the surface world with surface world knowledge of organisation and technology, disrupts this structure. He teaches the human tribes to cooperate, he introduces weapons and tactics, he forms alliances across tribal boundaries. He becomes, in the later books, the Emperor of Pellucidar, the organising force that brings the human inhabitants into something like a civilization capable of resisting the Mahars. This narrative of the civilizing hero is deeply characteristic of its era. Burroughs was writing in the early 20th century, in the middle of a period of intense popular interest in imperial adventure, and the structure of At the Earth's Core reflects that cultural moment without quite endorsing any particular political program. David Innes is not a conqueror in the conventional sense, he's more like a catalyst, someone whose arrival sets in motion changes that were already latent in the situation. The human inhabitants of Pellucidar do not need Innes to tell them that the Mahars are their oppressors. They know. What they need is the organisational knowledge and the technical capability that Innes brings from the surface world. In the fiction, this transfer of knowledge is presented as straightforwardly good. In retrospect, it is a more complicated story. The Pellucidar series ran to 7 novels, published between 1914 and 1944. The last one was incomplete when Burroughs died in 1950, leaving the interior world open and unfinished, its narrative threads dangling in the permanent noon of the central sun. The series became one of the foundational texts of the planetary romance genre, the genre of adventure stories set on other worlds, and its influence on subsequent science fiction is extensive. Concepts from Pellucidar appear, transformed and developed, in the work of later writers who were shaped by Burroughs' example. What made the series successful was not its scientific accuracy. It has none, not even the careful scientific pretense of Verne. It was the coherence and specificity of the world Burroughs created. Pellucidar is not merely a setting. It is a place with its own logic, its own rules, its own history that predates the arrival of any surface world character. The Mahars have their civilization and their records. The human tribes have their traditions and their rivalries. The geography has been there long enough for rivers to have carved valleys and seas to have settled into their shapes. The place feels old in the way that real places feel old, not because Burroughs provides extensive historical background, but because the details he provides are consistent with each other in the way that details of a real place are consistent. Burroughs also understood something about the Hollow Earth's appeal that neither Halley nor Verne had quite articulated. The reason people were excited by the idea of the Hollow Earth was not primarily scientific. It was not really about the mechanics of magnetic declination or the temperature gradient of the Earth's interior. It was about the possibility of another world, a world that was already there, not needing to be built or colonized, but existing, fully formed, beneath the one we knew. And in 1914, the surface of the Earth was nearly fully mapped. The blank spaces were shrinking. The unexplored territories were becoming fewer and smaller. The poles were being reached. The jungles were being surveyed. The deep ocean was being sounded. The age of surface exploration was drawing to a close, and with it something that had been a persistent feature of human experience for millennia. The possibility that over the next horizon there might be something nobody had ever seen. Pellucidar was the last horizon, a world that no map had covered, that no expedition had reached, that was accessible in principle but had not yet been accessed, and that once accessed, offered exactly the combination of danger and wonder and possibility that the closing of the surface frontiers was eliminating. Burroughs gave his readers a frontier precisely at the moment when the real frontiers were disappearing. That was not an accident. It was an intuition about what his readers needed. The Pellucidar novels were not scientific documents and did not pretend to be, but they were something that the scientific documents, Halley's paper, Euler's proposal, Symmes' petition, were not. They were vivid. They created a place that readers could inhabit, that they could return to, that they could lose themselves in. The Hollow Earth as science was, by 1914, almost certainly wrong. The Hollow Earth as story was still very much alive. and stories have a different relationship to evidence than hypotheses do. Evidence can disprove a hypothesis, evidence cannot disprove a story. Pellucidar still exists in the 7 novels, exactly as Burroughs described it. The central sun still hangs at the centre of the holosphere. The Mahas still rule. David Innes still navigates the politics of the interior world. Nothing that has been discovered about the actual interior of the Earth has any bearing on any of this. The story is made of different material than the hypothesis. The material it is made of does not interact with geological evidence. This is why the hollow Earth, as a popular idea, survived the scientific refutation that was approaching. The science was going against it. But the story was untouchable, and the story had, by 1914, reached a level of specificity and richness that was sufficient to sustain an independent life, sufficient to persist in the imagination regardless of what was happening in the seismology laboratories. Let Pellucidar settle around you for a moment, the permanent noon, the upward curving horizon, the central sun hanging motionless above. It is not real. But the person who made it real enough to sustain 7 novels, who sat in Illinois, having been a policeman and a cattle driver and a pencil sharpener salesman, and who made a world because the world needed making, that person was real. And the need that drove him was real. And the image he created, imprecise and scientifically impossible as it was, answered something in its readers that more precise and scientifically careful images had not quite reached. The scientific story of the hollow Earth was almost over, but the imaginative story, the story that is made of different material, that does not require geological accuracy to survive, that story has not ended yet. Burroughs himself became one of the most widely read novelists in the world during the 1910s and 1920s, not primarily because of the Pellucidar series, which was popular but not his most famous work, but because of another hollow geography he invented at almost the same time, Barsoom, the dying civilization of Mars that he began publishing in 1912. John Carter of Virginia, Confederate veteran and prospector, falls asleep in a cave in Arizona and wakes on the surface of Mars. The structure of the fantasy is identical to Pellucidar. A surface world man with ordinary surface world knowledge arrives somewhere extraordinary and becomes extraordinary there, but the setting is outer space rather than the inner Earth. Burroughs was mining the same desire from 2 directions at once, the desire for elsewhere, available in the direction of up as much as in the direction of down. The exhaustion of the surface map left 2 obvious directions for the imagination to move, and he moved in both simultaneously. Pellucidar went down, Barsoom went up. The geography was different, but the emotional structure was the same. Another world, accessible by improbable means, where the ordinary becomes extraordinary, and the self is remade by the encounter with the unknown. The remarkable thing is that both directions eventually became real in the way that scientific inquiry makes things real. The interior of the Earth, which Pellucidar had borrowed, was mapped by seismology. Mars, which Barsoom had borrowed, was mapped by probes and rovers. Neither was what the fiction had proposed, but both became known in the same way, by the patient, indirect method of observing effects and inferring causes, by instruments working at the edge of what measurement can reach. The imagination pointed. The instruments eventually followed. The answers were not the ones the imagination had proposed, but the pointing and the following were real. The 19th century was the great age of polar exploration, and the hollow Earth theory followed it closely, feeding on the expeditions, interpreting their findings through the lens of its premise, and occasionally shaping the questions that explorers were funded to answer. The connection between polar exploration and the hollow Earth was not incidental. Symmes had specifically proposed that the openings to the interior were at the poles. If he was right, then any expedition travelling far enough toward either pole would eventually find the lip of the opening, the gradual inward curve that he had described so carefully in his lectures and circulars. The explorers going north and south were, whether they knew it or not, approaching the edges of the question. The Arctic had been partially explored by Europeans since at least the 16th century, when the competition between England and the Netherlands for a northern sea route to Asia, a northwest passage or northeast passage that would allow ships to reach the markets of China and India without the long and expensive journey around the African Cape, had sent ships into waters nobody from those nations had previously navigated. The expeditions had been difficult and frequently fatal. The sea ice was unpredictable in its extent and its behaviour. The weather was extreme. Navigation was treacherous near the magnetic pole, where compasses gave increasingly unreliable readings. Sailors who entered the high Arctic in summer could find themselves iced in before they could retreat, spending long, dark winters in conditions that killed men through cold and scurvy and simple despair. Despite this, the expeditions continued. The motivations were partly commercial. The Northern Passage, if found, would be enormously valuable, and partly scientific and partly simply national prestige, the demonstration that a country's naval capacity extended to even the most forbidding waters. By the early 19th century, following the end of the Napoleonic Wars and the consequent freeing up of naval resources that had been occupied with European conflict for more than 2 decades, the British Admiralty launched an aggressive program of Arctic exploration. Ships and crews newly available for peaceful purposes were redirected toward geographical discovery, and the Arctic became the primary theatre for that discovery. The compass behaviour in the high Arctic was one of the phenomena that connected this exploration to the Hollow Earth debate. As ships travelled north of 70 or 75 degrees latitude, compass needles behaved in increasingly anomalous ways. The declination, the angle between magnetic north and true north, became very large. The needle also began to dip downward at a steepening angle, pulling toward the ice rather than pointing horizontally. Near the magnetic pole itself, the compass became essentially useless. The needle pointed straight down, attracted by the concentration of the magnetic field at the pole, rather than pointing toward any horizontal direction. This behaviour was not mysterious in principle. The geometry of a magnetic field produced by an internal dipole predicted that the field lines would converge at the poles and that a compass needle would follow those lines, dipping steeply in high latitudes. But the details of the polar magnetic behaviour were not yet fully worked out in the early 19th century, and to a mind predisposed toward Halley's nested sphere model, the anomalous behaviour of compasses near the poles was consistent with the approach to a region where the influence of inner spheres was becoming dominant. The hollow Earth provided an alternative explanation for the polar magnetic anomalies, one that was wrong, but that was not obviously wrong given what was known about magnetic fields in the 1820s. William Parry's expeditions into the Arctic in the 1820s produced some of the phenomena that hollow Earth advocates found most suggestive. Parry travelled farther north than any ship had previously managed, reaching latitudes where the behaviour of sea ice and weather did not conform to simple predictions. He found, in some locations, open water where theory predicted solid ice, what came to be called the open polar sea, a persistent belief that beyond a certain latitude the ice thinned and gave way to navigable open water at the pole itself. The open polar sea was, for a generation of explorers and theorists, a real feature of the polar geography, one that various expedition reports seemed to confirm, even though the reports were describing different things observed in different conditions and being interpreted through the lens of what people hoped to find. The open polar sea was not evidence for the hollow Earth. It was evidence for the complex dynamics of polar ocean circulation, for the way warm Atlantic water pushing into the Arctic could create pockets of relatively ice-free water in unexpected locations, for the seasonal variation in ice extent that made the same location ice-covered in winter and open in summer. But from a hollow Earth perspective, open water near the pole was exactly what you would expect. The approach to the opening through which interior warmth escaped would warm the surrounding sea and prevent ice formation. The hypothesis made a prediction, and the prediction seemed loosely to be confirmed. The most famous Arctic disaster of the 19th century, the Franklin expedition of 1845, sent 129 men under the command of Sir John Franklin into the high Arctic to find the Northwest Passage. HMS Erebus and HMS Terror were among the most advanced polar vessels of their time, strengthened against ice, equipped with steam auxiliary engines for navigation in heavy pack, supplied for 3 years of independent operation. Franklin and his crews sailed into the Arctic in July 1845 and were never seen by European eyes again. The search for Franklin became, over the following decade and a half, the most extensive program of Arctic exploration ever undertaken. More than 30 expeditions were sent to find him, by Britain, by the United States, by private individuals moved by the scale of the tragedy and the persistence of Franklin's wife, who lobbied for the search with extraordinary energy and effect. These expeditions mapped vast stretches of the Arctic that had never been charted. They found, eventually, the evidence that established what had happened. The ships had been trapped in ice north of King William Island. The crews had survived aboard through 2 Arctic winters, and then the surviving men had attempted to walk south across the ice and had died, one by one, of cold and starvation and lead poisoning from the soldered cans that had contaminated their preserved food. What the search for Franklin did not find, through all those expeditions across all that mapped ice, was any hint of a polar opening. Ships had penetrated into regions never previously visited. They had followed every lead, explored every channel they could navigate. They had found ice and rock and the tragic relics of the lost expedition. They had not found any indication of an inward curve, any anomalous warmth emanating from below, any suggestion that the geography was doing what Symmes had proposed it would do. But from the Hollow Earth perspective, this was not conclusive. Symmes had specified that the opening was at the pole itself, not adjacent to the pole, not near the pole, but at the precise geometric pole. No ship had yet reached the actual North Pole. The deepest penetration had stopped short of 80 degrees north. The pole was still roughly 1,000 miles away. The Hollow Earth hypothesis retained its fallback. The ship simply had not gone far enough. This particular structure, a hypothesis that retreats to exactly the territory that has not yet been explored, is a familiar one in the history of science. The evidence against the hypothesis expands as exploration expands, but the hypothesis contracts to exactly the unexplored region, always staying just ahead of the advancing frontier. It cannot be reached as long as there is anywhere unexplored, because it simply claims that the evidence is in the unexplored part. The only way to close the argument is to eliminate the unexplored territory entirely, to reach the pole and look. The American expeditions that followed Franklin's search began to push further north. Elisha Kane's expedition of 1853 to 1855 reached new high latitudes, and Kane himself reported observations that seemed, to Hollow Earth advocates, extremely suggestive. He described a large area of open water far to the north, the most extensive open water he had encountered, existing in a region where ice should, by all reasoning, have been thicker. He called it the open polar sea. It seemed to confirm that there was something different about the very high latitudes. Kane was wrong about what it was. The open water, he observed, was a seasonal and localized phenomenon, the product of Arctic circulation patterns, not of any interior warmth. But the report was real, and it was sincere, and in the absence of a better explanation, it fed the Hollow Earth speculation for another generation. The open polar sea was cited in arguments for the polar opening for decades after Kane's expedition, and long after the phenomenon had been explained by more prosaic oceanography. The actual North Pole was reached almost certainly by Robert Peary in April 1909, though the details of his claim have been disputed by historians in the century since, and the exact position he reached may have been slightly south of the true pole. The South Pole was reached by Roald Amundsen in December 1911, 5 weeks ahead of the ill-fated British expedition under Robert Scott. Both poles were solid. Both poles had ice rather than open water at the surface. Neither showed any indication of an inward curve, any suggestion of an opening into the interior. The polar expeditions had collectively explored the regions where the Hollow Earth was supposed to manifest most clearly, and found nothing. The poles were geography, not portals. The open polar sea was oceanography, not the breadth of an interior world. The anomalous compass behavior near the magnetic pole was the behavior of a planetary magnetic field, not the influence of inner spheres, but the definitive answer did not come from the poles. It came from a different direction entirely, from the patient analysis of waves that no explorer had felt, travelling through a planet that was, it turned out, considerably fuller than anyone had proposed. The Scott expedition that reached the South Pole in January 1912, 5 weeks after Amundsen, making the British party the second to the pole, not the first, found what every polar expedition before them had found at the edge of the unknown. Not an opening, not an inner world, but more of the same. Ice. More ice. Ice to the horizon in every direction, and the pole marked only by a tent Amundsen's party had left, with a note inside. Scott and his companions died on the return journey, overcome by cold and exhaustion, and a blizzard that caught them just 11 miles from a supply depot. They were not defeated by any mystery. They were defeated by a combination of bad luck and bad conditions on a continent that was exactly what it appeared to be: a cold, windswept, ice-covered landmass at the bottom of a solid planet. The tragedy of Scott's expedition ended the last chapter of polar exploration as adventure, in the 19th century sense. After 1912, no romantic notion of an open polar sea or a polar opening remained tenable in any serious quarter. The poles had been reached. They were geography. The hollow Earth had retreated to the only territory still available to it. Not the unexplored poles, but the unexplored interior, the region below the surface that no expedition could reach and no drill could approach. In this retreat to the subsurface, the hollow Earth was simultaneously defeated and preserved. Defeated because the most dramatic form of its claim, that polar openings existed that physical expeditions could find and enter, was now conclusively falsified. Preserved because the interior of the Earth was still, in 1912, largely unknown. The seismograph was developing, but the picture was not yet complete. The hollow Earth had been pushed out of the polar regions and into the Earth's interior, and the Earth's interior was still just barely ambiguous enough to provide a final refuge. That refuge lasted only 24 more years. When Inge Lehmann published her 1936 paper on the solid inner core, the refuge closed. Not because her paper addressed the hollow Earth, it did not. It was a paper about seismic wave analysis in a peer-reviewed scientific journal, with no reference to Symmes or Halley or any of the hollow Earth tradition. But it addressed the actual structure of the Earth's interior with enough precision to leave no room for a hollow. The Earth's centre was accounted for. The solid inner core sat there, detected by the behaviour of earthquake waves, occupying the space where the hollow would have had to be. The ice lies quiet now in the imagination. The ships have turned back. The men are below decks, warming their hands on tin mugs. Outside, the ice presses against the hull, with a sound like breathing. The compass needle dips toward the deck, doing what it always does in these latitudes, following the geometry of a field that does not care about theories. The pole is still ahead, still unreached, still maintaining its silence about what is or is not below it. But the silence is not going to last much longer. It is worth noting, before we leave the polar age entirely, how much the Franklin disaster shaped the cultural imagination of the Arctic in ways that outlasted the actual search. The image of Erebus and Terror locked in the ice, of 129 men slowly dying in the frozen dark, of the last survivors walking south across the sea ice until they could walk no further. This image was, for the Victorian public, the defining image of what the Arctic was. Not a place of mystery and possibility, a place of death, an environment so hostile that even the best equipped expedition that Britain could assemble was destroyed by it. This shift in the cultural imagination of the polar regions was not ultimately what ended the hollow Earth theory. The theory did not require the Arctic to be hospitable, only for the poles to have openings. But the Franklin disaster shifted the mood of polar exploration from adventure to tragedy, and that shift made the polar regions feel more like genuine geography, harsh, indifferent, deadly, and less like portals to mystery. The atmosphere of wonder that the hollow Earth required was harder to sustain after Franklin. The poles felt, after 1850, like places where people died, not places where worlds began. If you're using this to fall asleep, that's exactly why I make these videos. Maybe subscribe and let me know where you're watching from and what time it is. I always read the comments, and it's fascinating to see people from all over the world settling in at different hours, different seasons, different sides of the Earth. Anyway, back to the mystery. By the early 20th century, the hollow Earth theory had officially left the domain of serious science. The seismic evidence was accumulating. The polar regions were being systematically explored. The physics of the Earth's interior were being worked out through methods that Halley and Euler had not had available. The theory was not dead. Theories like this never quite die, but it had been displaced from its central position in the conversation about what was inside the Earth, pushed to the periphery, where it would spend the rest of the century. What happened to it there is strange and interesting in its own way. The 20th century hollow Earth tradition is not the tradition of Halley and Euler. It is not the tradition of serious natural philosophers working from incomplete data toward honest hypotheses. It is something else, a tradition of true believers, of people who hold the theory not as a hypothesis to be tested, but as a conviction to be defended, a truth to be protected from the distortions of official science. The transition from hypothesis to ideology is one of the more melancholy chapters in the story. One of the most persistent figures of the 20th century Hollow Earth world was an American named Marshall Gardner, who published a book called A Journey to the Earth's Interior in 1913, with a second expanded edition in 1920. Gardner, like Symmes, had no formal scientific training. Unlike Symmes, he was not proposing an expedition but a complete alternative cosmology, a view of the Earth and the solar system that differed from mainstream science in almost every particular. Gardner's Hollow Earth had a central sun like Euler's and polar openings like Symmes. But he went further. He argued that the aurora borealis and aurora australis, the northern and southern lights, were caused by light from the interior sun shining out through the polar openings. The auroras, in his model, were not caused by charged particles from the sun interacting with the Earth's magnetic field. They were the inner light made visible. The aurora explanation is telling. The actual explanation of the auroras, the one that's correct, requires an understanding of plasma physics, of the interaction between charged particles and magnetic fields, of the complex dynamics of the Earth's magnetosphere. It is not simple. It took decades of careful observation and theoretical development to work out fully. Gardner's explanation was simpler. The light comes out of the hole, and simpler, in the absence of the tools to evaluate the more complex explanation, can feel more satisfying. But by 1920, the tools existed. The aurora explanation was not fully settled, but it was far enough along that Gardner's polar opening alternative required ignoring a substantial body of evidence. He was not working from incomplete data toward an honest hypothesis. He was working from a conclusion backward to the data that fit it, and ignoring the data that did not. This is the methodological difference between a scientist and a true believer, and it matters. Gardner also argued that the mammoths found frozen in the Siberian permafrost, the remarkably preserved specimens that have been discovered since the 18th century, sometimes with flesh and stomach contents intact, were evidence for the Hollow Earth. His argument went like this. The mammoths lived inside the Hollow Earth, where the climate was warm enough to support vegetation year-round. Occasionally, mammoths would wander too close to the polar opening and fall out, landing on the Siberian surface and freezing in the permafrost. The frozen mammoths were, in his interpretation, tourists from the interior who had met with an unfortunate accident. The mammoth argument illustrates the characteristic structure of the late Hollow Earth tradition's engagement with evidence. Start with the evidence that needs explaining. Frozen mammoths are real. Their remarkably intact preservation genuinely does require a quick freezing event, and the question of why mammoths went extinct is a legitimate and still somewhat contested scientific question. Then attach the Hollow Earth explanation to that real question, proposing an interior world as the source of the evidence. The real question borrows legitimacy. The Hollow Earth explanation absorbs that legitimacy. Anyone who dismisses the Hollow Earth can be accused of dismissing the genuine question that prompted it. This rhetorical strategy, borrowing the legitimacy of a real scientific question to protect an unscientific explanation, is still common in various forms of alternative science. It works because the genuine question is genuine. Frozen mammoths do need to be explained, but the explanation that fits the evidence is not the Hollow Earth. It is the rapid climate change at the end of the last ice age, which created conditions, in particular the dramatic expansion of permafrost as climates became more seasonal, that could preserve carcasses before they decomposed. The mammoths that fell into bogs or sinkholes in early autumn could freeze before scavengers reached them and remain frozen for thousands of years. No Hollow Earth required. The 20th century Hollow Earth tradition also acquired in its later decades a connection to conspiracy thinking that had not been present in the earlier versions. The idea that official science was suppressing the truth of the Hollow Earth, that governments knew about the polar openings and were keeping them secret, began to appear in the 1940s and became dominant in the tradition by the 1950s. The reasons for this conspiracy are variously described depending on who is doing the describing. To prevent people from discovering the advanced civilizations inside, to maintain control over the resources of the interior, to protect military secrets, to avoid the theological implications of finding other inhabited worlds. The conspiracy frame changes the relationship to evidence in a fundamental way. A hypothesis that has not yet been tested can be falsified by testing. but a hypothesis that is protected by a conspiracy cannot be falsified by any available evidence, because any evidence against it can simply be attributed to the conspiracy. This silence of official science becomes evidence of suppression rather than evidence of absence. The failure to find a polar opening becomes evidence that the opening is being hidden rather than evidence that it does not exist. The theory becomes, in the technical sense, unfalsifiable. The most famous figure in the 20th century Hollow Earth conspiracy tradition is Admiral Richard Byrd. Byrd was a real person, a genuine American hero of polar exploration, who made multiple expeditions to the Arctic and Antarctic between the 1920s and 1950s, including the first flights over both poles. He was a legitimate explorer, decorated, respected, a figure of significant historical importance. The Hollow Earth tradition claims that Byrd's 1947 Arctic flight, a routine mission that he undertook as part of Operation High Jump, a large-scale Navy expedition to Antarctica, actually penetrated into the interior of the Earth through the polar opening and encountered an advanced civilization inside. This supposed encounter is described in elaborate detail in a document called Byrd's Secret Diary, which has circulated in Hollow Earth circles since at least the 1970s. The document is not authentic. Byrd's actual diaries and flight logs from 1947 exist. They are in the National Archives. They describe a perfectly ordinary military mapping expedition. The secret diary is a fabrication, a piece of fiction attached to a real person's name to borrow his credibility. Byrd himself never made any claim about a Hollow Earth encounter. He died in 1957, 12 years before the secret diary began circulating. The Byrd story is a useful case study in how the Hollow Earth tradition operates in its later conspiratorial phase. It takes a real person and a real event and attaches to them a fictional encounter, then claims that the real records have been suppressed. The real records are actually available. Anyone can request them from the National Archives. But in a tradition that requires conspiracy to function, the availability of contradicting evidence is simply evidence of how thorough the conspiracy is. There is also a tradition, developed largely in Germany in the early to mid-20th century, of a concave hollow Earth, the idea that we do not live on the outer surface of a sphere but on the inner surface, that what we think is outer space is actually the interior of a hollow Earth, and that the sun and stars are smaller objects floating at the centre. This theory, called Hohlweltlehre in German, was briefly taken seriously by some members of the Nazi Party. There is a story, probably apocryphal, of a radar experiment in 1942 aimed at bouncing signals off the inner surface of the concave Earth to detect the British fleet. The experiment reportedly failed. The story is likely embellished, but it illustrates how the Hollow Earth idea, in its various forms, attracted adherents who were looking not for truth, but for an alternative to the established order, in whatever domain that alternative was needed. The Hohlweltlehre was primarily developed by a German engineer named Cyrus Reed Teed, who later changed his name to Koresh, and founded a religious community in Florida called the Koreshan Unity. Teed claimed to have received the concave Earth theory through divine revelation in 1869. His followers conducted a surveying expedition in Florida in the 1890s, attempting to demonstrate that the Earth curved upward rather than downward, that a straight line extended along the ground would eventually meet the dome of the sky rather than departing into outer space. Their measurements, perhaps unsurprisingly, showed what they expected to show. The experiment was not independently reproducible. What connects the Koreshan Unity, the Nazi Hohlweltlehre, Gardner's Inner Sun, and the Byrd Secret Diary is not a single intellectual tradition. They are different groups, in different countries, with different specific beliefs, connected by the underlying desire for a different picture of the Earth than the one that mainstream science provided. The Hollow Earth served as a substrate for that desire in whatever form the desire took. It was, in this sense, not primarily a scientific theory at all by the 20th century. It was a social and psychological phenomenon wearing scientific clothing. The Nazi connection is sometimes used to discredit the Hollow Earth tradition entirely, as if the fact that some members of a repugnant political movement found the idea attractive proves that the idea is uniquely dangerous or deranged. This is not quite right. The Hollow Earth attracted those particular adherents for the same reason it attracted many others. It offered an alternative to mainstream science, at a time when mainstream science was, for various political reasons, suspect. The political valence of that suspicion is what varied. The underlying psychological structure, the desire for a different truth, a hidden truth, a truth that the authorities don't want you to know, is not unique to any political tradition. What is worth noting is that none of these 20th century traditions, the Gardner version, the Bird version, the concave Earth version, had any new evidence. They had the same evidence Halley had worked with, interpreted through the lens of a conclusion already reached, supplemented with fake documents and misread records and the persistent appeal of the unknown. The Hollow Earth was no longer a hypothesis, it was a mythology, and mythologies, as we have already discussed, are much harder to displace than hypotheses. You can disprove a hypothesis with evidence. A mythology absorbs evidence, interprets it, makes it fit, and continues. Let the slightly uncomfortable feeling of the conspiracy era pass. It is, in its way, part of the story, the part that shows what happens to a good hypothesis when the evidence goes against it and the advocates refuse to follow the evidence. Not every scientific idea that fails gets mythologized this way. Most simply, fade. The ones that get mythologized are the ones that were answering something deeper than a scientific question, something about the imagination, about the desire for hidden worlds, about the need to believe that the official picture is not the whole picture. The Hollow Earth was always answering something deeper than a scientific question. That is why it lasted. By the end of the 20th century, the Hollow Earth tradition had migrated to the internet, where it found a natural home. The qualities that had always sustained it, the ability to connect widely scattered believers, the production of documents and diagrams and testimonials, the construction of an alternative community of knowledge, were all qualities that the internet amplified. Hollow Earth forums, websites, and later social media communities allowed people with the belief to find each other, reinforce each other, and develop increasingly elaborate versions of the tradition without needing to rent halls or print pamphlets. The internet version of the Hollow Earth is not a single belief. It is a loosely connected cluster of beliefs, varying considerably in their specific claims. Some versions maintain the Symmes polar openings, others adopt the concave Earth model, some incorporate extraterrestrial beings living in the interior, some connect the Hollow Earth to specific religious prophecies, some are mainly interested in the conspiracy angle, in who knows about the Hollow Earth and why they are hiding it. The common thread is the basic premise. The official story of the Earth's interior is wrong, and the truth is being concealed. What is perhaps most striking about the Internet-era Hollow Earth community is how little the new evidence has mattered. The seismic data has continued to accumulate, becoming more precise and more comprehensive with each decade. The mineral physics experiments at high pressure have become more sophisticated. The global seismograph networks have multiplied and improved. The picture of the Earth's interior that these tools provide has become richer and more detailed. None of this has had any discernible effect on the Hollow Earth community. The evidence is not engaged with. It is dismissed as fabricated or misinterpreted, using the conspiracy frame that was established in the mid-20th century, and that has become, if anything, more entrenched in the Internet era. This resistance to evidence is not unique to the Hollow Earth. It is a feature of a broad class of alternative belief systems that share the conspiracy structure. The conclusion is fixed, the evidence is interpreted through the conclusion, and any evidence against the conclusion is attributed to the conspiracy that the conclusion requires. The Hollow Earth is one of the cleaner examples of this structure, because the evidence against it is so comprehensive and so independent, seismic data, gravitational measurements, drilling results, laboratory experiments at extreme pressure, that dismissing it requires dismissing most of what the physical sciences have built over the past century and a half. The Hollow Earth persists in these communities, not as a scientific theory but as a social identity. To believe in the Hollow Earth is to be part of a community that knows something the mainstream does not, that has seen through the official story, that trusts its own interpretation of reality over the pronouncements of institutions. The specific content of the Hollow Earth belief is almost secondary to this social function. What matters is the structure, the alternative community, the hidden truth, the official deception. These elements are stable across many different specific beliefs, and they provide something, a sense of belonging, of special knowledge, of resistance to authority, that the content of the belief cannot by itself provide. The answer came from earthquakes, not from expeditions to the poles, not from drilling, not from some dramatic discovery at the surface, from the patient, meticulous study of how vibrations travel through the planet, from the development of instruments sensitive enough to detect the faint echoes of distant seismic events, and from the slow, careful work of comparing those echoes to what physics predicted they should sound like if the Earth had one internal structure versus another. The science is called seismology, and its foundational instrument is the seismograph, a device for recording the motion of the ground, detecting vibrations too small for a human body to feel, translating those vibrations into a traceable record of how the Earth moved and when. The first practical seismographs were developed in the 1880s and 1890s. They operated on a simple principle: a heavy mass suspended so that it resisted the motion of the ground around it, while a pen attached to it traced the mass's relative motion against a slowly rotating drum of paper. When the ground moved, the drum moved with it, and the mass resisted, and the pen drew a wavy line on the paper that recorded the motion in time. These first seismographs were crude. They were sensitive to only a limited range of frequencies. They could detect large earthquakes clearly, but missed smaller ones entirely. They could tell you that the ground had moved, and roughly when, and roughly by how much. But the precise analysis of the wave patterns that would eventually unlock the Earth's structure required something more. Not just detection, but discrimination between different types of waves, and the mathematical tools to interpret what the discrimination revealed. When a large earthquake occurs somewhere in the world, a rupture along a fault, the sudden release of stress that had been accumulating for years or decades in the rock, it generates several types of seismic waves simultaneously, each carrying different information about the medium through which it travels. The primary waves, or P waves, are the fastest. They are compressional. They push and pull the rock in the direction they are travelling, like the compression and extension of a spring being pushed from one end. P waves are very good at travelling through almost anything: solid rock, liquid iron, the partially molten material of the mantle. They are the first waves to arrive at a distant seismograph after a major earthquake. The secondary waves, or S waves, are slower. They are shear waves. They move the rock sideways, perpendicular to their direction of travel, like the motion of a rope being shaken from one end. S waves are slower than P waves through the same material, and they have a critical limitation that turns out to be enormously important. They cannot travel through liquid. A shear wave requires the material it is travelling through to have a resistance to shearing, a property that solids have but liquids do not. When an S wave encounters a liquid layer, it is absorbed, reflected, or converted into other wave types. It does not pass through. This difference between P waves and S waves is the key that unlocked the Earth's interior. Richard Dixon Oldham was a British geologist working at the Geological Survey of India at the turn of the 20th century. In 1906, he published a paper in the Quarterly Journal of the Geological Society of London, in which he analysed the seismic records from multiple stations around the world following a large earthquake. He noticed something striking in the data. At distances greater than a certain angle from the earthquake's epicentre, the S waves did not arrive as expected. They were absent, and also weakened as to be effectively undetectable, in a zone that corresponded to waves that had travelled through the central region of the Earth. The P waves still arrived in this zone, delayed and refracted, but there, the S waves did not. The interpretation was inescapable. The central region of the Earth was liquid. S waves could not pass through it. Oldham had not gone there. No instrument had gone there. No drill had reached within thousands of kilometres of it. But the behaviour of the earthquake waves told him, unmistakably, that the Earth's centre was a liquid zone through which shear waves could not propagate. Oldham had detected the Earth's outer core, not by visiting it, not by drilling to it, not by any direct measurement, but by observing the shadow it cast in the paths of earthquake waves. The earthquake was a spotlight. The liquid core was an opaque object. The shadow revealed the object. This is indirect measurement at its most elegant, using the behaviour of waves to infer the properties of material they passed through. The hollow Earth hypothesis made a specific prediction about the behaviour of seismic waves. If the Earth were hollow, waves travelling through the interior would behave as if they were passing through empty space. Waves passing through empty space, a vacuum, do not travel at all because there is no material to carry them. If the hollow Earth hypothesis were correct, seismic waves aimed at the interior would simply disappear at the boundary of the hollow cavity and never emerge on the other side. What Oldham found was the opposite of this. Waves did travel through the Earth's interior, and their behaviour revealed not emptiness, but a specific material, a liquid of a specific density, at the centre. In 1909, a Croatian geophysicist named Andrija Mohorovičić, working in what is now Zagreb, analysed the records from an earthquake in the Kupa Valley and noticed something peculiar in the early arrivals. For earthquakes at certain distances, there were two distinct P-wave arrivals rather than the one expected. One arrived at the time predicted by a model in which waves travelled through uniform rock from source to receiver. The other arrived earlier, meaning it had travelled faster at some point in its journey than the rock near the surface could account for. Mohorovičić's interpretation was that the faster arrival corresponded to waves that had dipped down into a denser layer of rock beneath the surface crust, travelled through that denser rock at a higher speed, and then returned to the surface ahead of the wave that had stayed in the shallower, less dense rock the whole way. He was identifying a boundary between two layers of rock with different densities and different wave speeds. This boundary is now called the Mohorovičić discontinuity, the MOHO, and it marks the base of the Earth's crust. It is typically 30 to 40 kilometres below the surface of the continents, thinner under the oceans. In 1914, a German geophysicist named Benno Gutenberg, working with seismograph records from multiple global stations, pinpointed the depth of the boundary between the mantle and the outer core at approximately 2,900 kilometres below the surface. This is now called the Gutenberg discontinuity. At this depth, the rock of the mantle gives way to the liquid iron of the outer core, and S waves, which have travelled faithfully through the solid mantle, stop. These discoveries, the MOHO, the Gutenberg discontinuity, the liquid outer core, were assembled not by any single researcher, but by a community of scientists working across multiple countries and multiple decades, sharing data through the emerging international network of seismograph stations, comparing notes, checking each other's interpretations. The picture that emerged from this collective effort was a planet layered like an onion. Thin crust, thick mantle, liquid outer core, and, as Inge Lehmann would discover in 1936, something else at the very centre. Inge Lehmann was a Danish seismologist working in Copenhagen when she noticed, in the records of distant earthquakes, a systematic anomaly. Certain P-waves were arriving in a zone, the P-wave shadow zone, where the liquid outer core should have excluded them, where they should not have been able to arrive. They were faint, these unexpected arrivals, but they were real and they were consistent across multiple earthquakes and multiple recording stations. Something was refracting waves back into the shadow zone, bending them, changing their path in a way that was only possible if they had passed through a material with different properties than the liquid outer core. Lehmann proposed, in a paper published in 1936, that the explanation was a solid sphere at the centre of the liquid outer core. A solid inner core, approximately 2,400 kilometres in diameter, denser than the liquid surrounding it, capable of refracting waves in the way the data showed. The inner core reflected and refracted certain P waves back into the shadow zone, and those refracted waves were what her careful analysis had detected. The proposal was accepted gradually, as more data accumulated, and the predictions it made were checked against observations. The inner core is now one of the most confidently established features of the Earth's interior, detected by seismology, constrained by mineral physics experiments at extreme pressures, incorporated into every model of the Earth's dynamics that has been developed in the decades since Lehmann's paper. Lehmann herself lived to be 104, dying in 1993. She published important research into her 80s. The Inge Lehmann Medal, awarded by the American Geophysical Union for distinguished contributions to the study of the Earth's interior, was established in 1997 and continues to be awarded. She once described the work of seismology as comparable to detective work, reading the clues left by the Earth's behaviour to infer the structure that produced them, never visiting the scene directly, working always from evidence to interpretation. The hollow Earth could not survive the seismologists, not because the seismologists set out to disprove it. They were not, for the most part, engaging with the hollow Earth hypothesis at all. They were doing something more powerful than engaging with it. They were rendering it irrelevant by providing a positive, specific, detailed description of what was actually inside the Earth. The evidence was not absence of a hollow Earth. It was presence of something else, layers of rock and liquid iron and solid iron, each with measured properties, each leaving its signature in the behaviour of earthquake waves. The detective had found the answer. The case was closed. Below you the waves are moving now, always somewhere, because the Earth is always shaking somewhere. Small tremors that no human body notices. The waves radiate outward through the rock, reaching the liquid outer core and bending, reaching the solid inner core and refracting, travelling through the entire planet in minutes and emerging at seismograph stations on the far side as faint, precise records of everything they pass through. The Earth speaks continuously in the language of seismic waves. The seismologists learned to listen, and what they heard changed everything. What they heard was a planet full to the centre with material, with rock and liquid iron and solid iron compressed under pressures that do not exist anywhere on the surface. What they heard was not a hollow drum but a solid bell, and when a bell rings, it rings with the sound of everything it is made of. The development of the global seismograph network that made all of this possible is itself a story worth pausing over. In the 1890s, individual seismologists operated their own instruments at their own institutions, with no systematic coordination and no standard methods of recording or reporting. A large earthquake would produce records at a dozen different stations across Europe and Asia and America, but those records might be on different paper scales, with different time references, with different instrument configurations, making comparison extremely difficult. The scientists knew that the richest information lay in comparing records from many stations, that triangulating the arrival times of the same wave at many locations would reveal the wave's path through the Earth with great precision, but without coordination, the comparison was difficult. John Milne, a British geologist who had spent many years in Japan and who had observed the devastating earthquakes of that seismically active country, took the initiative in the 1890s of establishing what became the first global seismograph network. He distributed instruments of a standard design to observatories around the world, persuaded those observatories to report their data in a uniform format, and for decades personally compiled the incoming reports at his station on the Isle of Wight. When the great San Francisco earthquake of 1906 struck, Milne's network detected it clearly. When the seismic records from that event were analysed by Oldham, they provided some of the clearest evidence yet for the liquid outer core. The 1906 earthquake that produced Oldham's key discovery was the same earthquake that destroyed much of San Francisco in April of that year. The earthquake and the fire that followed it killed approximately 3,000 people and destroyed 28,000 buildings. While the catastrophe was unfolding on the surface, its seismic waves were travelling through the planet, arriving at instruments around the world, recording in their delays and diffractions the structure of the deep interior, disaster and discovery connected by the same event. The image that seismology provides of the Earth's interior is not a snapshot. It is a composite built up from thousands of earthquakes over more than a century, each one illuminating different paths through the Earth, each set of records adding detail to the picture. No single earthquake reveals the full structure. The picture emerges from the accumulation, from the patience of running many instruments for many years and assembling the data into a coherent whole. This is normal science, though it is rarely described this way. Not eureka moments, but decades of careful compilation, the picture sharpening slowly as more data arrives. There is something almost meditative about the seismologist's work in this sense, the patient waiting for the next earthquake, the careful reading of the records when it comes, the slow assembly of the picture from evidence that arrives in fragments, years or decades apart. The Earth does not reveal itself quickly. It reveals itself through time, to observers patient enough to wait for the evidence. The seismograph network that Milne helped establish has grown enormously in the century since his work. There are now hundreds of seismograph stations operating continuously around the world, many of them part of the global seismographic network, a coordinated international effort to monitor the Earth's seismic activity and use the data for scientific research. These stations are sensitive enough to detect earthquakes anywhere on Earth within minutes of their occurrence, and also sensitive enough to detect the ringing of the Earth itself, the way the entire planet vibrates at its natural frequencies in response to very large seismic events. When a magnitude 9 earthquake occurs, the kind that happens perhaps once a decade, it sends waves through the planet that cause the entire Earth to oscillate. The planet rings, in a very real sense, at frequencies determined by its size, its density structure, and the elastic properties of the materials inside it. These oscillations can be detected at stations around the world for days after the earthquake, gradually dying away as the energy dissipates. The pattern of frequencies at which the Earth rings is a precise diagnostic of its internal structure. The hollow Earth would ring differently, not slightly, but dramatically, at frequencies that would be immediately obvious to anyone comparing predictions for a hollow Earth against actual observations. The Earth does not ring at those frequencies. It rings at the frequencies of a planet with a solid inner core, a liquid outer core, and a thick mantle of solid rock. Every large earthquake that has occurred since the development of the global seismograph network has been, inadvertently, a test of the hollow Earth hypothesis. And the Earth has failed that test every time, in the most precise and reproducible way that a physical measurement can fail a hypothesis. There is a question that has been hovering over this story from the beginning, and it is worth naming directly before we move on. How did brilliant people believe something that turned out to be so fundamentally wrong? Not wrong in a minor way, not a decimal point in the wrong column, not a coefficient slightly miscalculated. Wrong in the most structurally basic way possible. The Earth is not hollow. It has never been hollow. The hollow Earth hypothesis was incorrect in its primary claim from the very first moment it was made. How, then, did Halley, whose other work was correct and significant, propose it in all seriousness? And how did Euler, whose mathematical judgment was nearly infallible, take it up and develop it? The answer requires being careful about what kind of question we're asking. If the question is, were Halley and Euler less intelligent than people who came later and knew better, then the answer is clearly no. The problem was not intelligence. If the question is, were they careless or sloppy, motivated by something other than the pursuit of truth, then the answer is also no. Both men were scrupulously careful in their methods. Halley's Atlantic voyage to measure magnetic declination was expensive and dangerous, and he undertook it because he believed the measurements mattered. Euler's mathematical analysis of the hollow Earth's physical implications was rigorous, and he would have been the first to abandon the model if the mathematics had shown it to be internally inconsistent. The answer is simpler and more interesting than either of those alternatives. They were working in genuine ignorance of information that had not yet been gathered, and they were doing the only thing available to people who must reason about something they cannot directly observe. They were constructing a model that fit the evidence they had. A scientific model is not a description of reality. This is a distinction that is easy to lose sight of, because when models are good and familiar, when they have been tested repeatedly and found to work, they begin to feel like descriptions of reality, as solid and reliable as the things they describe. But a model is, properly understood, a proposed description of reality, a way of organizing observations into a coherent picture that generates testable predictions. The test of a model is not whether it is beautiful or elegant or intuitively satisfying. The test is whether its predictions match observations, all the observations, including observations that have not yet been made. Halley's model passed the test available to it. It organized the observations of magnetic declination into a coherent pattern. It made predictions about the rate and pattern of secular variation that could be checked against compass records. It predicted that measurements made in different parts of the world would show different rates of drift in ways that fit the nested sphere model. When Halley and his successors checked these predictions against the available data, the fit was reasonable. The model worked, in the sense that it produced predictions consistent with what was being observed. The problem was that other models could also fit the same data. The secular variation of magnetic declination is a real phenomenon that required and requires explanation. But the same observations that fit Halley's nested sphere model also fit other models. In particular, they fit the model of a liquid outer core in constant convective motion, with its motion driving the changes in the magnetic field that Halley observed. Halley's model and the correct model make the same predictions about the observable phenomenon of magnetic declination. They differ in what they propose is happening inside the Earth to produce that phenomenon. This is the deepest scientific lesson of the Hollow Earth story. matching the data is necessary but not sufficient. A model can be consistent with all available data and still be wrong, because the available data may not be discriminating enough to choose between multiple models that all fit it. The hollow Earth matched the available data in 1692. The real structure of the Earth also matches that data. The data alone, the data available in 1692, could not choose between them. What eventually enabled the choice was different data. Not more of the same kind, not more compass readings, not more observations of magnetic declination at different locations. Different kinds of data entirely. Seismic wave behavior, the measurement of the Earth's density through gravitational experiments, the laboratory study of rock properties at extreme pressures and temperatures. Each new kind of data narrowed the range of models that could be simultaneously consistent with everything observed, until finally only one structure remained viable: the crust, mantle, liquid outer core, solid inner core. The process of getting from Halley's 1692 paper to Lehmann's 1936 discovery of the inner core took 2.5 centuries. This seems like a long time, but consider what it required. Not just better instruments, though that was part of it, but entirely new disciplines: seismology as a quantitative science, mineral physics as an experimental field, global observation networks, mathematical frameworks for interpreting wave behavior. None of these things existed in 1692. Most of them did not exist in 1818. The accumulation of tools and knowledge that made the answer possible was the work of multiple generations of researchers, most of whom were not thinking about the hollow Earth at all but were simply advancing their own fields. This is how knowledge actually accumulates, not in a straight line from question to answer, with the questioners knowing from the start which direction to walk, in a broad front with researchers advancing different tools in different directions, gradually surrounding the question from multiple angles until the question space is exhausted, until every possible structure has either been ruled out by evidence or confirmed by it, and only one possibility remains. Halley's mistake is worth distinguishing carefully from the mistakes of the 20th century hollow Earth advocates, because the distinction matters morally and methodologically. Halley proposed a hypothesis. A hypothesis is a proposed explanation held tentatively, submitted to scrutiny, subject to revision or abandonment in response to evidence. Halley knew he was speculating. He said so explicitly in his paper. He was not claiming to have visited the hollow Earth. He was claiming that the hollow Earth, as he had modelled it, would produce the observations he'd catalogued, and that if the model was wrong, better data would show why. The 20th century hollow Earth advocates were doing something different. They were defending a conclusion against evidence. The seismic data had spoken, the polar expeditions had spoken, the density measurements had spoken. The evidence against the hollow Earth was not merely suggestive, it was comprehensive, precise, and consistent across multiple independent lines of investigation. The advocates' response to this evidence was not to update their model. It was to propose that the evidence had been falsified, suppressed, or misinterpreted by a scientific establishment committed to hiding the truth. This is not how Halley operated. Halley was wrong. The 20th century advocates were wrong. But they were wrong in entirely different ways. Halley was wrong in the way that science sometimes is, reasoning correctly from insufficient information to an incorrect conclusion. The 20th century advocates were wrong in the way that ideology always is, reasoning from a conclusion to whatever evidence seemed to support it, and dismissing whatever evidence did not. Euler, in particular, deserves consideration on his own terms. His hollow Earth was not his primary claim about the world's structure. It appeared in a broader philosophical work as one of several possible models, a possibility to be explored, a hypothesis to be calculated through, not a conviction to be defended. He was not the kind of thinker who staked his identity on any particular answer. He was a mathematician who explored problem spaces. If the hollow Earth turned out not to work, mathematically or empirically, Euler would have moved on to the next problem. The inner sun was interesting precisely because it raised interesting mathematical questions. The questions were worth exploring whether or not the answer they implied was correct. There is something valuable in this attitude that is worth holding on to, especially when we are wrong. The exploration of wrong hypotheses, done carefully and honestly, produces knowledge. Not the knowledge the hypothesis claimed to provide, but knowledge about the structure of the problem, about what the evidence does and does not support, about the range of models that are consistent with what is known. Euler's calculation of the gravitational dynamics of an inner sun may never have led anyone to conclude that there actually was an inner sun, but it contributed to the development of the physics of self-gravitating systems, which is a real and important area of knowledge. Wrong answers in this sense are not wasted. They are the scaffolding around which right answers are eventually constructed. The hollow Earth raised questions about the Earth's interior that required answering. The answers, when they came, were not hollow Earth answers. But the questions were the right questions, and the data gathered to address them was real data, and the real data ultimately told the real story. This is the nature of the scientific process at its best. A community of people asking questions, proposing answers, testing those answers against evidence, revising them when the evidence demands revision, and accumulating over time and across generations a picture of reality that is more accurate than any individual mind could have produced alone. Halley could not have discovered the geodynamo, he did not have the tools, but without Halley's observation of secular variation, the geodynamo might have taken longer to become a priority, and the instruments needed to understand it might have developed more slowly. The hollow Earth was a wrong turn on the path to the right answer. Wrong turns are part of paths. They are not failures of the path. They are features of how paths through complex terrain actually work. What this means, lying here in the dark, is something small and possibly comforting. The questions you cannot yet answer, the things you do not yet understand about the world or about yourself, are not waiting in a void. They are waiting in a space that is being approached from multiple directions by inquiry that is already underway. The data is being gathered, the instruments are being refined, the models are being compared to the evidence. The answer is approaching from more directions than you know. You do not have to hold the answer yet. You only have to hold the question clearly and honestly and let the process work. There is a philosopher of science named Imre Lakatos who made a distinction that is useful here between what he called progressive and degenerative research programs. A progressive research program is one that keeps generating new predictions, new questions, new ways of engaging with the world. One that, even when specific hypotheses within it turn out to be wrong, leads its researchers toward better and more accurate formulations. A degenerative research program is one that has stopped generating new predictions, one that exists only to protect its central claim from refutation, adding auxiliary hypotheses to explain away disconfirming evidence without generating any new observations or testable claims. Halley's Hollow Earth was, in its original form, part of a progressive research program. It generated specific predictions about the pattern of secular magnetic variation, about what expeditions to the polar regions would find, about the behavior of the magnetic field at different locations. These predictions could be tested, and testing them, even when the hollow Earth turned out not to be where the tests pointed, generated new data and new questions. The hollow Earth as a scientific hypothesis was a progressive failure. It failed, but it failed in ways that moved the inquiry forward. The 20th century hollow Earth was a degenerative research program. It had no new predictions. It had no new observations to offer. It explained all evidence against it as conspiracy or misinterpretation, and it offered no independent test that could distinguish itself from any other theory that made the same move. It was not generating knowledge. It was simply persisting, protected by the unfalsifiability that the conspiracy frame provided. The transition from Halley's Hollow Earth to the conspiracy Hollow Earth is the transition from a progressive to a degenerative research program. What began as a genuine scientific proposal, testable, specific, held honestly, became, over 2 centuries, something that had lost the capacity to be wrong. The loss of the capacity to be wrong is the loss of the capacity to learn. A belief that cannot be falsified is not really a belief about the world. It is a belief about oneself, about one's identity, about one's relationship to authority. The content has become secondary to the structure. This is not a peculiarity of the hollow Earth. It is a pattern that appears across many domains where scientific inquiry runs into the edges of what current tools can test. The question is always, when the evidence comes in against your model, do you follow the evidence or defend the model? Halley, if he had lived long enough to see the seismic data, would have followed the evidence. The choice tells you something about the character of the inquiry, not just its correctness. There is one more distinction worth drawing before we move on, between the kind of not knowing that Halley represented and the kind of not knowing that the 20th century Hollow Earth advocates represented. Halley's not knowing was honest. He did not know the answer. He proposed a hypothesis. He held it as a hypothesis. His not knowing was productive. It generated inquiry, gathered data, asked questions that the next generation could try to answer with better tools. The 20th century not knowing was, in a different sense, dishonest. It was not genuine uncertainty about the answer, but certainty about a conclusion combined with rejection of the evidence that spoke against it. It did not generate inquiry, it blocked it. It gathered no data, asked no new questions, produced nothing that could be checked by an independent observer. The distinction between honest not knowing and defensive certainty is one of the most important distinctions in the practice of inquiry of any kind, scientific or otherwise. Honest not knowing is the foundation of learning. Defensive certainty is its enemy, and the difference between them is not always visible from the outside. Both can look like conviction, both can look like confidence, both can attract followers who find the appearance of certainty reassuring. The difference shows over time in whether the inquiry moves forward or whether it simply circles the same claim indefinitely. Halley's Hollow Earth moved forward. It moved forward all the way to Ing Lehmann's solid inner core and Benno Gutenberg's core mantle boundary and the understanding of the geodynamo that eventually explained the very phenomenon Halley had spent his life studying. The hypothesis was wrong. The inquiry it launched was right, and the rightness of the inquiry outlasted the wrongness of the hypothesis by as much time as separates us from the first planting of crops. Halley was wrong about what caused the drift of the compass needle. The nested spheres rotating at differential rates were not there. But what he observed was real, and the investigation it set in motion eventually led to an understanding of something that turns out to be one of the most consequential facts about the Earth, that it is wrapped in an invisible magnetic field generated by the churning liquid iron of its outer core, extending far into space beyond the atmosphere, and without which the surface of the planet would almost certainly not be the kind of place where you or anything like you could exist. The geomagnetic field, the Earth's magnetic field, is the thing that makes compasses work. Sailors have used it to navigate for 1,000 years without knowing anything about what produced it. They knew the field existed because they could measure its effect on a magnetized needle. They knew it varied with location and over time because their records showed it. But the mechanism, the process inside the Earth that generated the field and kept it going over geological timescales, was simply unknown until the 20th century provided the tools to figure it out. The mechanism is called the geodynamo. Inside the liquid outer core, the iron and nickel are in constant motion, convecting upward as they shed heat toward the cooler mantle above, and simultaneously being pushed into rotating patterns by the spin of the planet, the rotation imparting a systematic structure to what would otherwise be chaotic turbulence. This combination of convection and rotation in a liquid that conducts electricity generates electrical currents. Electrical currents generate magnetic fields. The magnetic fields interact with the motion to generate more complex motion. The whole system feeds back on itself in a self-sustaining way. Once it started, billions of years ago, it has continued without requiring any external input beyond the planet's rotation and the heat flowing out of the inner core. The dynamo that operates in your car's alternator or in the turbines of a power plant works on the same principle. Mechanical motion in a conductor generates electricity, which generates magnetism, which can be used to generate more mechanical motion. The geodynamo is the planetary scale version of this principle, operating in liquid iron rather than copper wire, sustained by heat and rotation rather than by combustion or falling water, generating a field large enough to be felt at the surface and to extend tens of thousands of kilometers into space. The field is not static. This is the thing Halley noticed, the secular variation of magnetic declination, and his observation was correct in every detail except the cause. The field does drift. The magnetic poles move. The magnetic North Pole has been drifting generally northward and recently westward, moving across Canada at rates that have varied over the past century. In the 1990s, it was moving at roughly 15 kilometers per year. By the 2010s, the rate had accelerated to approximately 55 kilometers per year, fast enough that navigational charts have needed to be updated more frequently than in earlier periods, because the error between magnetic north and true north is changing fast enough to matter to navigation. The reason the poles drift is not mysterious. given the geodynamo picture. The liquid outer core is in constant complex motion, and the magnetic field it generates reflects that motion. As the flow patterns in the outer core shift, as convection cells reorganize, as the rotation of the inner core relative to the outer core changes slightly, as heat flow from the mantle shifts over geological time, the field changes, slowly by human standards, but continuously. The secular variation that Halley measured was real evidence of these shifts. He was reading the geodynamo without knowing he was reading it. The field also reverses, entirely, completely, fundamentally reverses. North becomes south, south becomes north. This is perhaps the most dramatic fact about the Earth's magnetic history, and it was not known until the development of paleomagnetism in the mid-20th century. As lava cools and solidifies, the magnetic minerals in it align with the prevailing magnetic field at the moment of cooling. They become tiny, permanent compasses, frozen in place, pointing toward whatever direction north was when the rock formed. When geologists analyze the magnetic orientation of volcanic rocks of different ages, they find that the polarity reverses at irregular intervals, sometimes after a few 100,000 years, sometimes after millions of years with no predictable schedule. The most recent polarity reversal was approximately 780,000 years ago, in an event called the Brunhes-Matuyama reversal. The field did not switch instantaneously. It weakened over a period estimated at a few thousand years, during which it was confused and multidirectional, with multiple poles appearing at different locations before the field reorganized in the opposite polarity. During this weakening, the field's protection of the surface against the solar wind was significantly reduced, though whether this had significant effects on life at the time is debated among scientists. The evidence for past reversals is preserved in the oceanic crust in a form so clear and so systematic that it provided one of the key pieces of evidence for plate tectonics. At mid-ocean ridges, the underwater mountain ranges where the ocean floor is continuously being created as plates separate, new oceanic crust is formed from lava that wells up from the mantle and solidifies. As this new crust cools, it records the magnetic field at the moment of cooling. As the plates spread apart, the crust moves away from the ridge, carrying its magnetic record with it. The result on both sides of every mid-ocean ridge is a pattern of magnetic stripes, bands of normal polarity alternating with bands of reversed polarity, symmetric on both sides of the ridge because both sides are made of the same rock formed at the ridge and spreading in opposite directions. This striped pattern was identified in the early 1960s by geologists Frederick Vine and Drummond Matthews, and independently by Lawrence Morley, and it became one of the crucial pieces of evidence that confirmed the theory of seafloor spreading, and with it, plate tectonics. The stripes were a record of geological time, each stripe a period of one polarity, each transition between stripes a reversal. By comparing the width of the stripes to the known rate of seafloor spreading, geologists could construct a timeline of polarity reversals going back hundreds of millions of years. The Earth's magnetic history became, through the oceanic crust, legible. Halley, whose observations began all of this by asking the question of why the magnetic declination varied, did not know any of what would eventually be found. He could not have known. The concept of plate tectonics would not exist for 2.5 centuries after his paper. The oceanic magnetic stripes that confirm seafloor spreading were discovered 270 years after he measured the Atlantic's magnetic declination from the deck of the Paramore. The connection between his careful observations and the modern understanding of the Earth's interior and its surface dynamics is real, but enormously stretched in time, the kind of connection that is only visible when you have the perspective of centuries. The other great consequence of the geomagnetic field, its role in protecting the surface from the solar wind, is worth dwelling on, because it is easily overlooked when thinking about what the magnetic field does. The solar wind is a continuous stream of charged particles flowing outward from the sun in all directions. It is not gentle. It carries enough energy to strip away planetary atmospheres over geological timescales if the planet has no magnetic shield to deflect it. The evidence for this is visible in our solar system. Mars, which does not have a significant global magnetic field, also does not have a significant atmosphere. Venus, which is much closer to the Sun and also lacks a global magnetic field, has retained a thick atmosphere because of its size and its position, but but it has been dramatically altered by solar-wind interactions over billions of years. Earth has kept its atmosphere, the thin layer of air that makes possible every breath you have ever taken, in part because the geomagnetic field deflects the solar wind before it can interact significantly with the upper atmosphere. The field extends far into space in a region called the magnetosphere, a vast bubble shaped by the interaction between the Earth's field and the solar wind. On the sun-facing side, the magnetosphere is compressed by the solar wind pressure to a distance of roughly 60,000 kilometers. On the night side, it stretches away in a long magnetotail that extends millions of kilometers away from the sun. The solar wind flows around this bubble, deflected, most of its particles turning aside without reaching the upper atmosphere. When the solar wind is particularly intense, during solar flares or coronal mass ejections, when the sun ejects large quantities of charged particles at higher energies than usual, it compresses the magnetosphere more strongly, and some particles leak through at the poles, where the field lines converge and create relative vulnerabilities in the shield. These leaked particles interact with the upper atmosphere, exciting the gas molecules and making them emit light. This is the aurora, the northern lights and southern lights that glow in polar skies in green and white and red. The aurora is, in this sense, the visible signature of the Earth's magnetic field doing its job, deflecting the solar wind at the edges where the deflection is not quite perfect. Halley saw the aurora. He observed it from England during a particularly spectacular display in 1716 and wrote a paper about it, proposing that it was caused by luminous matter escaping from the Earth's interior through cracks near the poles. This is almost exactly wrong about the mechanism, but it contains a genuine insight. The aurora is connected to the interior of the Earth through the magnetic field generated by the outer core. Halley had the connection right. He had only the direction of the causal chain reversed. The aurora as the breath of an interior world, escaping through polar openings, this was one of the images that Hollow Earth advocates would return to again and again in the 19th and 20th centuries. Marshall Gardner's 1913 book specifically proposed that the auroras were the light of the inner sun shining out through this polar opening. The image is wrong, but it is not meaningless. There is a real connection between the auroras and the Earth's interior. The connection is the geodynamo, the field generated by the liquid outer core that deflects the solar wind, whose interaction at the polar regions produces the aurora. The interior is involved, just not in the way the Hollow Earth advocates thought. This is a pattern worth noticing in the Hollow Earth story. Many of the phenomena that Hollow Earth advocates cited as evidence, the auroras, the anomalous compass behavior in high latitudes, the secular variation of magnetic declination, the occasional warmth of polar ocean currents, were real phenomena that were genuinely connected to the Earth's interior. The advocates were not entirely making things up. They were looking at real evidence and inferring wrong causes. The real causes, when eventually worked out, turned out to be more interesting and more complex than the Hollow Earth, but they shared the basic feature that the Hollow Earth hypothesis was trying to point to. The inside of the Earth is active and consequential. It is doing things that matter for the surface. Halley was reading the Earth's interior in its effects on the surface. He was just reading it in the only language available to him, before the development of the languages, seismology, mineral physics, paleomagnetism, that would eventually make the reading much more precise and much more revealing. Let the aurora move in the imagination for a moment. Green light in a dark sky, rippling slowly. The charged particles from the sun meeting the Earth's field at the polar edge of the magnetosphere, being deflected, their energy converted to light. The light consequence of the outer core's churning, the dynamo's work made briefly visible at the edge of space. The inner and the outer connected by the invisible field, always, in all directions, even here in this room, bending around you and extending away into the dark. The geomagnetic field as it exists now is not the same field that existed when Halley was alive. It is not weaker or stronger in a simple linear sense. The field oscillates over time, strengthening in some periods and weakening in others. But by some measures, the field today is about 10% weaker than it was in 1600. Whether this is the beginning of a polarity reversal, or simply a normal oscillation, is a question that geophysicists are actively studying. The field has been weakening gradually for the past few centuries, and there is a region over the South Atlantic, called the South Atlantic Anomaly, where the field is already significantly weaker than at similar latitudes elsewhere, creating a region where satellites and spacecraft are more vulnerable to radiation damage from cosmic rays that the field does not deflect. This weakness at the South Atlantic anomaly is thought to be related to the complex dynamics of the outer core beneath it, a region where the convection patterns produce a local weakening of the field above. Whether it will continue to grow and contribute to a polarity reversal, or stabilize and eventually reverse, is not yet predictable with confidence. The geodynamo is a chaotic system, sensitive to initial conditions, producing complex and not fully deterministic behavior over long timescales. The uncertainty about the field's future is not alarming in any practical sense. Polarity reversals have occurred hundreds of times in the Earth's history. Life has survived all of them. The field does not switch off during a reversal. It weakens and becomes confused with multiple poles before reorganizing in the opposite direction. The process takes thousands of years, not days or centuries. There is no reason to think the next reversal, whenever it comes, will be catastrophic for life. But it is a reminder that the field Halley observed, the field that bent his compass needle and set him thinking about nested spheres, is not a permanent fixture of the world. It is a product of ongoing physical processes inside a planet that is still slowly cooling, still processing the heat of its formation, still in the middle of a 4.5 billion year story whose ending is not yet written. The compass needle is still drifting. The story is still going. Halley was watching something that has not yet resolved, and will not resolve, on any timescale that matters to anyone now alive. We have followed the hollow Earth from Edmund Halley's cold room in 1692 to the seismographs of the early 20th century that finally settled the question. We have watched it move from serious scientific hypothesis to popular obsession, to literary setting to conspiracy mythology. We have seen it attract some of the greatest minds of several centuries and some of the most determined true believers of others. We have seen it fail, definitively, as a physical description of the planet's interior. What remains is a question that is harder to answer than the geological one. Why did the idea have such a hold? Not just on the cranks and the true believers, but on the serious scientists who first proposed it, the careful mathematicians who elaborated it, the gifted writers who imagined it into fictional life, the ordinary readers who were moved by those novels and those theories in ways that simple geological error cannot explain. Part of the answer is simply filling a gap. The inside of the Earth was unknown. The unknown inside of the Earth was a real space, bounded above by the ground we stood on, extending downward for thousands of kilometers. It was not an abstraction. It was a place, in the most basic geographical sense. And the human mind, when confronted with a real place that it cannot see, does what it has always done. It imagines what is there. It fills the invisible with something, with myth, with hypothesis, with story, with speculation. Because the alternative is to sit with a blank, and blanks are uncomfortable in a way that extends beyond the merely aesthetic. But the hollow Earth was a very specific kind of filling, not just something is down there, which is the most that a purely logical inference could deliver. It was something interesting and potentially habitable is down there, something with structure, with warmth, with light, with the possibility of a life. The hollow Earth was a way of filling the blank below, not just with matter but with meaning, with the hope that the Earth was more than it appeared to be from the surface. This hope has a name in the study of human psychology and culture, the hope for elsewhere, the hope that there is more world than is currently accessible, that beyond the mapped and measured and categorized world, there is another world, older, stranger, less compromised by the processes that have made the familiar world familiar. This hope is ancient. It takes different forms in different periods and cultures, but it's recognizably the same desire, for a place that is not here, that is different from here in ways that are transformative, that offers possibilities not available in the familiar world. The island beyond the horizon, the land beyond the mountains, the city under the sea, the kingdom inside the hill, the space between the stars. Each of these is a culturally specific form of the same underlying desire, and each of them is, in its specific way, a response to the same specific situation, the exhaustion of the available unknown. The desire for elsewhere is most intense when the elsewhere is being eliminated, when the blank spaces on the map are shrinking, when the last unexplored territories are being surveyed and named and incorporated into the familiar world. The hollow Earth emerged as a serious scientific hypothesis in 1692, at the moment when the age of European exploration was well advanced, but the interior of the Earth was still entirely unknown. It flourished through the 19th century, exactly the period when the surface of the Earth was being mapped most aggressively, when the Arctic and Antarctic were being explored, when the great interior regions of Africa and Asia and South America were being surveyed, when the blank spaces on the map were visibly shrinking year by year. It became a popular obsession precisely when the other forms of elsewhere were being eliminated. The hollow Earth was the last blank space, immune to the surveyor's chain because no chain could reach it, immune to the cartographer's grid because no grid could be projected through thousands of miles of solid rock. Jules Verne understood this, which is why Journey to the Centre of the Earth works not just as an adventure story, but as an emotional response to a specific historical moment. Professor Leidenbrock descends not just because he is curious about the interior of the Earth, but because he needs to go somewhere that has not yet been mapped, measured, and reduced to the familiar. The underground sea is, among other things, a fantasy of the unmapped, of being the first person to see something that no map has covered, of experiencing a geography so new that it has no name. Burroughs understood this even more explicitly. He published at the Earth's core in 1914, the year that the last significant blank spaces on the surface map were being filled in, the year the Antarctic continent had been reached, the year the polar regions were known to be solid geography rather than portals to the interior. Pellucidar was the last elsewhere available to a world running out of elsewheres, and Burroughs filled it with exactly what the exhaustion of surface elsewheres left his readers hungry for: danger, wonder, primitivism, the possibility of arriving somewhere new and mattering there in ways that ordinary surface life did not permit. The fantasy of mattering is part of the hollow Earth's appeal that tends to get overlooked. David Innes, in the Pellucidar series, arrives in the interior world as a wealthy young man with no particular distinction on the surface. He's not a military hero or a great scientist or a political leader. He's someone who happened to finance a mechanical drill. But in Pellucidar, his surface world knowledge is extraordinary. He knows things that nobody in the interior world has ever known. That the sky's a limit rather than a floor. That the sun moves rather than being fixed. That time passes and can be measured. That human beings can cooperate in the complex ways that civilization requires. These ordinary pieces of knowledge, ordinary on the surface, are revolutionary in Pellucidar. They make Innes significant in a way that he could not be at home. This fantasy of arriving somewhere that your ordinary competence would be extraordinary competence, of being needed in a world that had never encountered anyone like you, is deeply appealing in a way that goes well beyond adventure fiction. It speaks to the universal experience of feeling ordinary in a world that is already well supplied with people, already organized along lines that leave most individuals with limited scope for the kind of transformative significance that the imagination reaches for. The hollow Earth offered, in its various fictional forms, a world where you could start over, where the particular combination of knowledge and personality and energy that you happen to have would be more than sufficient for what was needed. The scientific tradition of the hollow Earth, Halley's tradition, the tradition of serious inquiry into the planet's structure, was doing something slightly different, but not entirely unrelated. It was also reaching for a world beyond the accessible one, but the reach was cognitive rather than geographical. The unknown world was the interior of the Earth as a physical system, a domain of processes and structures that produced observable effects, but whose internal workings were hidden. Understanding that system, mapping it, as it were, with the instruments of measurement rather than the instruments of navigation, was its own form of reaching for elsewhere. The hollow Earth was what Halley's cognitive imagination filled the unknown interior with, before the tools existed to fill it with something more accurate. Both the scientific and the literary versions of the hollow Earth were responding to the same fundamental situation: the existence of a real unknown, a real blank in the map of the world, and the human need to do something with that blank other than leave it empty. The difference was in the tools available and the standards applied. Halley used the tools of natural philosophy and held his proposal to the standard of internal consistency and empirical adequacy. Verne used the tools of narrative and held his proposal to the standard of sensory vividness and emotional plausibility. Burroughs used the tools of adventure fiction and held his proposal to the standard of imaginative coherence. a standard that required only that the world he built be consistent with itself, not with any external reality. All three versions failed in different ways to match the actual interior of the Earth, but all three were genuine responses to the same genuine unknown, and all three contributed in different ways to the tradition of thinking about what was below. Without Halley's scientific formulation, the hollow Earth would not have had the credibility to attract the attention it received. Without that attention, the questions it raised would not have been pursued with the rigour that eventually answered them. Without the literary versions, Verne's and Burroughs and the dozens of others, the hollow Earth would not have been part of the cultural vocabulary that made the geological discoveries feel significant rather than merely technical. There is a connection between the literary hollow Earth and the scientific one that is easy to miss. Verne's novel did not just popularise the idea of a hollow Earth, it also popularised the idea that the Earth's interior was worth taking seriously as a scientific domain, that the question of what was below was not just a mythological question or a philosophical one, but a question that science could and should address. The novel's careful engagement with the actual geological debates of its time sent readers to those debates who would otherwise never have encountered them. Some of those readers became scientists. Some of those scientists went on to contribute to the fields that eventually answered the question. This is the strangest and perhaps most interesting part of the hollow Earth's legacy. The wrong idea, imagined vividly enough and spread widely enough, created part of the cultural demand for the right idea. The readers who fell in love with Verne's underground sea and Burroughs' Pellucidar were people who cared about what was below the surface of the Earth. That caring, that investment in the question, that desire for the answer, was part of the social context that made it possible to attract funding and attention, and young researchers to the fields that actually settled the question. You cannot make a discovery without caring about it, and caring is not produced by evidence alone. It is produced by imagination, by story, by the specific and vivid rendering of what a discovery might mean. The hollow Earth, as story, was part of what kept the scientific question alive long enough for the scientific question to be answered. The hollow Earth was a wrong answer, but it was a productive wrong answer, one that kept attention focused on a real question, that motivated real inquiry, that created a cultural context in which the real answer, when it arrived, was received as significant rather than merely technical. This is the most charitable interpretation of the hollow Earth's legacy, and I think it is also the most accurate one. There is a kind of sorrow in following this story to its conclusion, not sorrow for the hollow Earth, which was wrong and deserved to fail, but sorrow for the desire it was answering, the desire for another world available below, the desire for a place not yet mapped, not yet named, not yet incorporated into the familiar, the desire that drove Halley's careful hypothesis and Symmes' exhausting lecture tours and Verne's meticulous imagination and Burroughs' proliferating sequels was a real desire pointing at a real need, and that need did not disappear when the hollow Earth was disproved. What happens to the desire for elsewhere when elsewhere runs out? When the poles have been reached and found to be solid geography, when the oceans have been charted and found to have no openings, when the interior of the Earth has been mapped by earthquake waves and found to contain iron rather than civilizations. The desire does not disappear. It redirects into the oceans, which remained genuinely mysterious below their surface well into the 20th century. Into space, which replaced the hollow Earth as the preferred location for the unknown once the surface of the Earth was fully mapped. Into the quantum scale, the very small, which turned out to be as strange and unintuitive as any imagined underworld. Into time, into the past, which can be explored by archaeology and paleontology and the study of ancient documents in ways that yield genuine surprises. The hollow Earth was one form of the desire for elsewhere. It is gone now, not because the desire went away, but because the specific blank it occupied has been filled. The elsewhere it offered is no longer available, because the interior of the Earth is now known. But the desire itself survives, looking for new blank spaces, new unknown territories, new places where the imagination can reach past the boundary of the mapped and find something that has not yet been categorized. This is perhaps the most human thing about the hollow Earth story. Not the wrongness of the theory, not the colourfulness of its advocates, not even the extraordinary rightness of the scientific answer that replaced it. The most human thing is the persistence of the desire, the refusal of the imagination to accept that all the blanks have been filled, the insistence that somewhere, below or beyond or inside some system of knowledge we haven't yet constructed, there is still an elsewhere worth reaching for. Let it settle now. The wrong answer and the question it kept alive. The blank that was filled, first with myth and then with hypothesis and then with story and then, finally, with accurate knowledge. The candle that went out in Halley's room and the seismographs that are still running right now in dozens of countries, recording the whisper of the Earth's interior activity, all of it part of the same long conversation about what is below. All of it evidence, in its different ways, of the same desire to know what is there even when getting there is impossible. The real inside of the Earth deserves its own chapter, not because it needs defending against the hollow Earth theory, which has already been settled, but because it is, on its own terms, one of the most remarkable things that patient inquiry has ever uncovered. The picture assembled by 2 centuries of seismology and geophysics is not a disappointment. It is a discovery, and like most discoveries, it is stranger and more interesting than the guesses that preceded it, more dynamic, more violent, more strange in the particular ways that reality tends to be stranger than imagination. Begin with the crust, the layer you are resting on, more or less directly, separated from you only by the floors and foundations and soil of wherever you are. The crust is thin, embarrassingly thin, relative to the planet as a whole. Under the continents, it is between roughly 30 and 70 kilometers thick, the variation reflecting the geological history of different regions, with old, cold cratons supporting thicker crust and recently active volcanic regions having thinner. Under the oceans, the crust is thinner still, typically 5 to 10 kilometers, made of denser basaltic rock rather than the lighter, more granitic rock of the continental crust. This thickness, 30 to 70 kilometers for continental crust, 5 to 10 for oceanic, might sound substantial, but relative to the radius of the Earth, which is approximately 6,371 kilometers, the crust is comparable in proportion to the skin of an apple. Everything that human beings have ever directly experienced, the deepest mines, the highest mountains, the ocean trenches, the volcanic systems and hydrothermal vents and cave systems, is all within this thin skin. The vast majority of the Earth's volume, and the processes that make the surface what it is, are all below it. Below the crust, the mantle begins. The mantle is solid rock, but it does not behave in ways that the word solid usually suggests. It is hot enough, and the timescales over which it exists are long enough, that it flows, not like water flows, more like an extraordinarily stiff glass. Given enough time and enough pressure, it deforms and moves. The speeds are measured in centimeters per year, comparable to the speed at which a fingernail grows. But given millions of years, those centimeters accumulate into the grand motions of plate tectonics, continents separating and colliding, ocean basins opening and closing, mountains rising and eroding and being replaced by new mountains. The mantle is the largest component of the Earth by volume. Approximately 84% of the planet's total volume is mantle. It extends from the base of the crust down to approximately 2,900 kilometers, where the outer core begins. The rock it is made of is dominated by minerals called silicates, compounds of silicon, oxygen, magnesium, iron, and other elements, and its properties change significantly with depth as pressure increases and mineral structures rearrange themselves to pack more tightly under the weight of the rock above. The heat-driving mantle convection comes from 2 sources. Some of it is primordial, heat trapped inside the planet when it formed from the accretion of material in the early solar system. The energy of countless collisions converted to heat and slowly leaking outward over the 4.5 billion years since formation. Some of it is radiogenic, generated by the slow radioactive decay of elements, including uranium, thorium and potassium, which are present in trace amounts throughout the mantle, and which have been releasing their decay energy as heat since the planet formed. The relative contributions of these 2 sources are still debated among geophysicists, but both are real and both are significant. Deep within the mantle, seismic tomography, the technique of using earthquake waves from many directions to build a 3-dimensional image of the mantle's internal structure, has revealed features that nobody anticipated. 2 vast regions near the base of the mantle, one beneath Africa and one beneath the Pacific, are anomalously slow for seismic waves. the waves travel through them more slowly than through the surrounding mantle, indicating that these regions are hotter and possibly chemically different from the material around them. These features, called large, low shear velocity provinces, extend for thousands of kilometers in each direction and have been present, in roughly their current form, for hundreds of millions of years. What are they? Nobody is entirely certain. One theory holds that they are compositionally distinct, that they are remnants of early Earth material that never fully mixed into the rest of the mantle, surviving as large blobs of different rock through billions of years of mantle convection. Another theory holds that they are purely thermal, hot regions where mantle material has accumulated, possibly fed by deep processes at the core mantle boundary. A third possibility is that they are partially molten, that the combination of a high temperature and distinctive composition has pushed them close to their melting point, producing the seismological anomaly. The large low shear velocity provinces are also associated with the plumes that produce hotspot volcanoes at the surface. Hawaii sits above a mantle plume, a column of anomalously hot rock rising from deep in the mantle, that originates, according to some research, at or near the edge of the African low shear velocity province, travelling upward through the mantle over tens of millions of years before erupting at the surface. Yellowstone, Iceland, the Galapagos Islands, many of the world's anomalous volcanic regions are thought to overlie plumes that trace back, deep in the mantle, to one of these two anomalous provinces. Below the mantle, the outer core begins. Liquid iron and nickel, at temperatures between roughly 4,000 and 5,000 degrees Celsius, under pressures of between 135 and 330 gigapascals, numbers so extreme that they require pause. 1 gigapascal is approximately 10,000 atmospheres. The pressure at the bottom of the deepest ocean trench is roughly 0.1 gigapascals. The pressure at the base of the mantle is 3,000 times that. Under these conditions, iron is liquid despite temperatures lower than the sun's surface, because the pressure keeps the atoms from moving freely enough to vaporize but high enough that they cannot arrange themselves into the ordered structure of a solid. The liquid outer core is the source of the Earth's magnetic field as we have discussed, but it is also the source of something else worth noting. The heat flowing upward from the outer core into the mantle is one of the drivers of mantle convection and, through mantle convection, of plate tectonics. The outer core is not isolated from the surface dynamics. It is connected to them through the mantle, through the convection it drives, through the plates it moves. The iron churning 6,000 kilometers below your floor is connected to the mountain range outside, to the earthquake that shook the city last century, to the volcanic island that rose from the sea a million years ago. Everything is connected through the mantle, in both directions. And then at the very center, the inner core, Inge Lehmann's discovery, a solid sphere of iron and nickel approximately 2,400 kilometers in diameter, slightly smaller than the Moon, sitting at the precise center of the planet. The temperature at the center of the inner core is estimated at between 5,100 and 6,000 degrees Celsius. The pressure is approximately 360 gigapascals, 3.6 million atmospheres. Under these conditions, iron is solid, not because it is cool, but because the pressure prevents the atoms from adopting the disordered arrangement of a liquid. The iron atoms are forced into a specific crystalline structure that, at lower pressures, would require much lower temperatures to maintain. The inner core is not simply a static object. Evidence suggests that it rotates slightly faster than the rest of the Earth, perhaps completing an extra full rotation relative to the surface every 400 years or so. This differential rotation was detected through careful analysis of how seismic waves from earthquakes at one location on the Earth's surface arrive at the seismograph station on the opposite side. Waves that pass through the inner core in one direction arrive slightly differently from waves that pass through it in another direction, in a way that is consistent with the inner core having an asymmetric structure and rotating relative to the mantle above it. The inner core is also, somewhat surprisingly, not entirely uniform. Seismic waves travel through the eastern hemisphere of the inner core, the hemisphere that faces Asia and the Pacific, slightly differently than through the western hemisphere. The reason for this asymmetry is actively debated. It may reflect differences in the crystal structure of the iron between the two hemispheres, perhaps caused by the inner core growing slightly faster in one region than another, or by the interaction between the inner core and the liquid outer core above it. Whatever the cause, the inner core has a structure, an internal architecture, that is still being mapped with the tools of seismology, still not fully understood. A little-known feature of the inner core is the boundary layer that surrounds it, at the very bottom of the liquid outer core, a region of partially solidified material that is more complex in its physical state than either the fully liquid outer core above or the fully solid inner core within. This region, sometimes called the mushy zone, or the inner core boundary layer, is where the iron is in the process of solidifying, where individual iron crystals are growing and forming the solid inner core from the liquid above. The growth rate is extremely slow. The inner core is growing by perhaps 1 millimeter per year as the Earth continues to cool, but it is continuous, and it has been continuous for the billions of years since the inner core first formed. The age of the inner core is a matter of ongoing scientific debate, but estimates generally fall between 1 and 2 billion years. This means the inner core is younger than the Earth itself, which is 4.5 billion years old. Before the inner core formed, the outer core was entirely liquid. The formation of the inner core, the first solidification of iron at the planet's centre, was likely a significant event in the Earth's magnetic history, potentially affecting the strength and structure of the geomagnetic field. All of this, every feature of the Earth's interior from the moho to the inner core, is known from the surface, not from visiting, not from drilling, from the careful interpretation of earthquake waves, gravitational measurements, laboratory experiments at extreme pressures, and the long, patient comparison of many independent lines of evidence. The inside of the Earth has never been visited. The deepest hole ever drilled, the Kola Super Deep Borehole in northwestern Russia, a project that ran from 1970 to 1994, reached 12 kilometers before technical difficulties halted it. 12 kilometers, less than 1/5 of the way through the crust. The mantle, the outer core, the inner core, all of these are known entirely from the outside through their effects on things that can be measured at the surface. This is not a limitation of the knowledge. It is, in a way, the most impressive feature of it, that such precise and comprehensive understanding of something so remote could be built entirely from indirect evidence. That the behavior of earthquake waves arriving at surface seismographs could reveal, with enough precision to debate the crystalline structure of the iron at the planet's centre, the complete internal architecture of the Earth. The hollow Earth imagined a world below that was empty enough to be accessible, hollow enough to contain seas and jungles and civilizations, accessible through polar openings to anyone willing to travel far enough. The real Earth is the opposite, dense all the way to the centre, full in the way that things are full when 4.5 billion years of gravity has done its work, compressed under pressures that make every familiar physical intuition unreliable. The real Earth is not accessible in the way that Symmes' hollow Earth would have been. It is not available for exploration in any conventional sense. And yet it is known, not visited, but known, not mapped with physical presence, but mapped with something more extraordinary than physical presence, with the patience of wave physics and the precision of modern seismographs and the mathematical frameworks that connect them. The inside of the Earth is the most thoroughly characterized place that human beings have never been. That is, if you sit with it, quite remarkable. Let it settle. There is one feature of the actual subsurface that comes closer than almost anything else to vindicating the hollow Earth advocates' intuition, if not their specific claims, about what was down there, the deep biosphere. Life exists below the surface of the Earth at depths and in conditions that were entirely unexpected before the middle of the 20th century. Bacteria and archaea, single-celled microorganisms, have been found in rock pores at depths of 3 kilometers and more below the surface. They live without sunlight, drawing energy from chemical reactions between the rocks and the water that percolates through them, reactions that release hydrogen or methane or sulfur compounds that the microorganisms can use as fuel. The biomass of the deep biosphere, the total mass of living material below the surface, is difficult to estimate precisely, but some estimates suggest it may be comparable to the total biomass of all surface life, though this is debated. The organisms that make up this subsurface biosphere are, in many cases, extraordinarily slow-living. Some bacteria in deep rock formations are estimated to divide only once every few thousand years. Their metabolism is so slow that it barely qualifies as metabolism in any sense familiar from surface biology. They are, in some sense, barely alive, but they are alive, and they have been alive, some of them, for periods that stretch into the geological past. The deep biosphere does not vindicate the hollow Earth. The organisms that live below the surface are not the advanced civilizations or prehistoric animals of the hollow Earth tradition. They are single-celled microorganisms, barely visible under a microscope, living in rock pores so small that a human hair would block them. But they do vindicate, in a strange and limited way, the intuition that life might persist below the surface, in conditions that the surface world would not support. The subsurface is not sterile. It is inhabited in its own extraordinary way, just not in the way anyone imagined. And the hot springs that appear at the surface, the geysers and hydrothermal vents and volcanic hot springs, are windows into the subsurface energy budget in a different way. The heat that drives them comes from below. The chemistry that makes the water strange and valuable to the organisms that live around it comes from the deep reactions between water and rock, from the heat of the mantle below, from processes that connect the deep interior to the surface in ways that the hollow Earth advocates were dimly sensing when they proposed that warmth from below explained polar anomalies and open water in the Arctic. The inside of the Earth is connected to the surface, not through hollow spaces or polar openings, but through heat flow, through volcanic activity, through the geomagnetic field, through the mantle convection that drives plate tectonics. The hollow Earth advocates were right that the inside mattered for the outside. They were wrong about the mechanism. The mechanism, once understood, turned out to be richer and more consequential than any hollow they had proposed. We are near the end now. The story has come the full distance, from Halley's compass in 1692 to the seismographs of the early 20th century, from the first careful scientific proposal to the definitive geological answer, from the imagined hollow world to the real and extraordinary solid one. Before the sleep fully arrives, it is worth pausing over the figures who appeared in this story, holding each of them for a moment before letting them go. Edmund Halley lived until 1742, dying at the age of 85, which was remarkable for any period and extraordinary for the 17th and 18th centuries. He was Astronomer Royal for the last 20 years of his life, the official scientific observer of the British Crown, directing the Royal Observatory at Greenwich with the same careful attention he had brought to everything. His comet returned, as he had predicted, in 1758, 16 years after his death. He never saw the confirmation. He knew, when he wrote his prediction, that he would not. He wrote it anyway, because the prediction was correct whether he lived to see it confirmed or not. This is worth sitting with. Halley proposed the hollow Earth in 1692 and spent the next 50 years observing, calculating, publishing, and never saw the hollow Earth theory either confirmed or definitively refuted in his lifetime. The tools that would eventually settle the question did not yet exist. He died with the question open, as most people who ask significant questions do. The inquiry outlived the inquirer, as it almost always does. Leonhard Euler died in 1783 in St. Petersburg at his work table. He had been blind for 17 years by that time. His left eye had been lost at 26, his right eye at 59, and he had spent those 17 years producing mathematics with the help of his prodigious memory and the assistance of family members who wrote down what he dictated. On the day he died, he had been calculating the orbit of the newly discovered planet Uranus and playing with his grandchildren. He died as he would have wished to, in motion, engaged, still reaching. Euler's collected works, the Opera Omnia, fill more than 80 volumes and are still being edited and published. He is the most prolific mathematician in history, and many of the notations and concepts he developed remain standard. When you see the letter E in a mathematical context used as the base of natural logarithms, you're using Euler's notation. When you see the notation fx for a function, you're using Euler's notation. The hollow Earth was one small and incorrect proposal among the tens of thousands of correct ones. John Cleves Symmes died in 1829 in Hamilton, Ohio, at the age of 49, having never organized the polar expedition he dreamed of, and never received the congressional funding that would have made it possible. He was buried in Hamilton, and his tomb is marked with a stone monument carved in the shape of the hollow Earth, a globe with holes at both poles, representing the openings he insisted were there. The monument still stands. People visit it. Whatever you think of the theory, he was a man who believed something completely and spent his life in its service, and there is a kind of integrity in that. even when the belief is wrong. Jeremiah Reynolds, who fell away from Symmes but not from the vision, eventually got his polar expedition, not as a Hollow Earth expedition, but as the United States Exploring Expedition of 1838, the first American naval voyage organized explicitly for scientific purposes. It spent 4 years in the Pacific and Antarctic, charted 280 islands, collected specimens that became the foundation of the Smithsonian Institution's collections, and confirmed that Antarctica was a continent. Reynolds did not sail with it, having been removed from the planning committee, but his advocacy was part of what made it happen. The Hollow Earth route to the Antarctic was wrong. The Antarctic was real. Richard Owen, the geologist who most harshly dismissed Symmes in the popular press, became one of the most influential scientists of the 19th century, coining the word dinosaur in 1842 and founding the Natural History Museum in London. He was also a complicated figure, prone to credit disputes and scientific vendettas, and he was wrong about evolution in ways that Symmes, who died a decade before Darwin's work, at least was never wrong about. Being correct about the Hollow Earth was not the sum of Owen's scientific life. Inge Lehmann, who in 1936 proposed the solid inner core from her analysis of seismic data from the 1929 New Zealand earthquake, lived until 1993, 104 years old. She continued working until her late 80s, contributing to seismology and geophysics across a career that spanned most of the 20th century. She received the William Bowie Medal, the highest honor of the American Geophysical Union, in 1971, and the Bowie Medal citation described her as someone who had shaped the field more than any other person of her generation. She was the first person to see, clearly and correctly, what was at the very center of the Earth. These people, Halley, Euler, Symmes, Reynolds, Lehmann, and the dozens of others who contributed to the question and its answer, were not characters in a story about the Hollow Earth. The Hollow Earth was an episode in their lives, and in some cases not the most important episode. They were people who lived in specific times and places, who worked with what they had, who were right about some things and wrong about others, who built on what came before them and left behind things that others would build on. What connects them, across the 3 centuries of this story, is that they were all paying attention to the same question: what is below? Not in the same way, not with the same tools, not to the same ends. But the question was the same question, and each of them, in their way, moved the answer forward, by proposing something testable, by gathering data, by developing new tools, by refusing to accept the inherited answer when the evidence pointed elsewhere. The Hollow Earth failed as an answer, but the question it was trying to answer, what is the structure of the Earth's interior? How does it work? Why does the magnetic field drift? What produces the heat that comes up from below? Those questions were real. They were the right questions, and they have been answered in the 2.5 centuries since Halley first formalized them, with extraordinary precision. The crust, the moho, the mantle, the outer core, the inner core, the geodynamo, the secular variation explained, the auroras understood, the plate tectonics revealed by the magnetic stripes on the seafloor. The specific connection between the beginning and the end of this story is worth stating clearly, because it is the most satisfying postscript that history has provided. Halley's original observation, the thing that prompted the Hollow Earth hypothesis in the first place, was the secular variation of magnetic declination, the slow drift of the compass needle over decades and centuries. He needed a mechanism that could produce this drift. The nested spheres were his proposed mechanism. In 2003, a group of geophysicists studying the differential rotation of the inner core published a paper in Science, connecting inner core rotation to the secular variation of the Earth's magnetic field. The slight differential rotation of the inner core, the fact that it rotates very slightly faster than the outer Earth, gaining perhaps 1 extra rotation every 400 years, contributes to the pattern of magnetic field changes that produces secular variation. The slow rotation of the interior relative to the surface, a differential rotation, just as Halley proposed. Halley was right that the cause of secular variation was a differential rotation of the Earth's interior. He was wrong about what was rotating, not nested spheres, but the solid inner core within the liquid outer core. He was right that the mechanism was dynamic, that it involved the interior of the Earth moving in a way that the surface did not move. He was wrong about the form of that motion. The observation was correct. The category of explanation was approximately correct. The specific model was wrong. This is, if you are inclined to see it that way, a kind of posthumous vindication, not of the hollow Earth, which remains definitively refuted, but of Halley's intuition that the secular variation was caused by something moving inside the Earth in a way that the surface did not move. He was reaching toward the right idea with the wrong model. The right model came 250 years later. The idea he was reaching toward was real. The Earth turns beneath you. The inner core turns very slightly faster, gaining its fraction of a degree with each passing year. The outer core churns, driven by heat from below and the planet's rotation, its convecting currents generating the magnetic field that wraps around the Earth and bends out into space. The mantle flows, imperceptibly slowly, carrying the continents on its surface in their slow drift. The crust, the thin skin that separates all of this from the surface where you rest, conducts the heat upward, slowly, the same heat that has been flowing since the planet formed. You are resting on something extraordinarily active, not hollow, not available to be filled with a competing world, with inner suns or underground seas or civilizations of reptile people who never heard of Darwin. Full, dense with rock and liquid iron and the crystalline iron of the inner core, alive with processes that operate on timescales that dwarf any human time frame but that are, in the language of physics and geology, active and continuous and vigorous. The dream of the hollow Earth was the dream of another world available below. The actual Earth has something different to offer, a real world below, not accessible to exploration in the ordinary sense, but known, mapped by the patience of earthquake waves and the careful minds who learn to read them. Stranger than the hollow Earth ever managed to be, because reality has no obligation to be imaginable, and the interior of the Earth has taken full advantage of this freedom. Consider what you would need to explain if you tried to explain the actual Earth to someone from 1692. You would need to explain that the ground beneath their feet is a thin shell, resting on a mantle of rock that flows like an extremely slow fluid, driven by heat from a liquid iron core that acts as a giant electrical dynamo, surrounded by a solid iron sphere at the center that rotates slightly independently of the rest of the planet. You would need to explain that this system generates an invisible magnetic field that wraps around the entire Earth and extends far into space, deflecting a constant stream of charged particles from the Sun, and that without this deflection the atmosphere would be slowly stripped away over geological time, making the surface uninhabitable. You would need to explain that the thin rock shell, the crust, is divided into about a dozen large pieces, the tectonic plates that are in constant slow motion, carried along by the convecting mantle beneath them, that where two plates collide, mountains are pushed up, that where one plate dives beneath another, volcanoes appear above the diving plate, that where plates separate, new crust is created from material welling up from the mantle below, that the continents are where they are because of the positions of these plates, and that the positions have changed enormously over geological time, that the Atlantic Ocean is still widening at roughly the rate that your fingernails grow, and that it will continue to do so for tens of millions of years. A person from 1692 would, if they were scientifically minded in the way Halley was, find all of this considerably more extraordinary than the hollow Earth. It is a world of hidden processes, invisible dynamics, vast timescales, and structures inaccessible to direct observation but nonetheless precisely known. It is, in other words, exactly the kind of world that Halley was reaching toward when he proposed the hollow Earth, a world in which the observable surface is only a small part of what is actually going on, and in which the deeper story, the real story, requires instruments and inference and patience to uncover. He just got the specific version of that story wrong. The general intuition that what is below is active and consequential and connected to what is above was exactly right. The compass needle in Halley's room swings slightly from where it pointed when he was young. It is still drifting. The inner core is still turning. The geodynamo is still running. The question he asked in 1692 has been answered, and the answer is more extraordinary than the hollow Earth ever was. Let the descent complete itself, through the crust, through the moho, through the vast slow mantle, past the transition zone where minerals rearrange under pressure, down to the outer core where iron moves in the dark and generates the field that protects everything, and finally to the centre, the solid inner core, hot enough to be plasma but held solid by pressure, slowly turning, the innermost point of the innermost thing, approximately 6,371 kilometres directly below wherever you are. That is where the Earth ends, that is what is there, and now, at last, you can rest. Thank you so much for watching. I hope the story gave you something to think about as you drifted, both the strange and earnest wrongness of the hollow Earth, and the stranger and more satisfying rightness of what is actually down there. If you made it this far, and the video is still playing, and you're still hovering at the edge of sleep but not quite gone, let the image stay with you for a moment, the compass needle in Halley's room, still drifting, even now, as it has been drifting for as long as the geodynamo has been running, pointing to a magnetic north that is itself moving slowly as the liquid iron of the outer core shifts its patterns and the magnetic field shifts with it. The needle does not know about the hollow Earth, or about the liquid core, or about Inga Lehmann, or about you. It simply follows the field as it always has. There is something comfortable in that, if you let it be. The Earth's interior processes do not require anyone's attention to continue. The mantle is flowing right now, has been flowing without pause for billions of years. The outer core is churning. The inner core is turning, very slightly faster than everything above it, gaining its fraction of a degree. The field wraps around the planet in every direction, including the direction where you are. None of it requires anything from you. It simply continues. If you enjoyed this video, the subscribe button is somewhere visible on your screen. Or if you're listening in the dark, you can always find the channel later. I release a new documentary every week. Always something curious. Always something that rewards the long, slow attention of a quiet night. There are other mysteries waiting. Other stories from history, from science, from the strange edges of what people have believed and what they have discovered. But for now, the question I want to leave you with, if you could ask Edmund Halley just one question, knowing what we know now about what is actually inside the Earth, what would you ask him? Leave it in the comments if you feel like it. I read every one. The room is dark, the Earth is full all the way down, sleep well. If you want to leave something in the comments, a question for Halley, a thought about what surprised you in the story, where you're watching from and what time it is there, I always read them. There is something I find genuinely moving about the pattern of those comments. People from every continent, every time zone, at all hours of the night and early morning, all using the same long story to find their way to sleep. A kind of community in the dark, which seems appropriate for a story about the things that exist in the dark below us. The Hollow Earth was, in the end, not a story about the Earth at all. It was a story about the human need to believe that the known world is not the whole world. That need is real. It will always find something to attach to, some blank space, some unknown territory, some place where the imagination can reach past the edge of what has been confirmed and propose something more. The Hollow Earth was one of those propositions. It was wrong. But the need it was answering was not wrong. The need it was answering is the same need that has driven every scientific discovery, every geographical exploration, every artistic act of imagining a world that does not yet exist but might. The comet will come back. It always comes back. Halley worked that out in 1705, calculating the orbit from historical records and predicting the return date with such precision that the prediction was confirmed after his death. The comet did not know about Halley. It did not care about his predictions or his other work or his hollow Earth. It simply continued on its orbit, following the mathematics that Halley had worked out, returning as he had said it would. The universe is not altered by our models of it. Our models are altered by the universe, when we pay careful enough attention. Sleep well. The field is still there, bending around you in every direction, generated by the churning iron of the outer core protecting everything. You do not need to think about it. It simply continues, as it has continued for billions of years, as it will continue for billions more. You're held, in the most literal electromagnetic sense, by processes that began long before you existed and will continue long after. There is something restful in that, if you let it be. Good night. The field is still bending around the room where you are. The inner core is still turning. The outer core is still churning in the dark. These processes require nothing from you. not attention, not belief, not awareness. They simply continue, as they have for billions of years, while you sleep.